This is going to be a little bit disorganized, at least from the jump, because I ran into some technical difficulties. My computer just completely crashed like 20 minutes ago. And so I had to plug my laptop in for everything. And so I'm missing my notes and like everything I had to prepare for this. But I have, a generally good outline of what I had in mind to go over. Same way we've been doing this before. If you have questions, feel free to ask them in the chat. Shane will be able to handle that. Shane, you're welcome to interrupt me as well. If it seems like multiple people are wondering the same thing, or if you have something you just want to chime in on as we're going through here. The goal of this meeting is a little bit different than the ones that we've done to this point. I haven't taught this like this before, so this is a little bit experimental. My goal is to go through tips that I have for hacking the ChemPhys section of this test. Many of you have talked to me and heard me say that I think that ChemPhys is probably the most hackable section on the test. So part of what I have planned out here today is to show you why I think that. We're going to talk about ways of approaching problems on the ChemPhys section, specifically math on the MCAT. I think gives a lot of people a hard time on ChemPhys. So I'm going to go through some just general tips that I think are really useful whenever approaching any sort of quantitative problem on this exam. Also going to talk about my personal approach that I made up to approaching ChemPhys questions that you're not really sure what to do on, because that ends up being a decently large number of questions on the MCAT that you're just not really sure exactly how to begin approaching it. So I have kind of a hierarchical order of moving through things. And then if we have time at the end, we're going to read through a ChemPhys passage. I might have to scramble to pull one up because I had all of this prepared before my computer crashed like 20 minutes ago. Also, if you want to, you can turn your cameras on, but you definitely don't have to. I don't want to pressure you into that. It is a little bit easier to get kind of an interactive thing going if you do have them on. However, if I were you, I probably wouldn't turn it on because I'd be up moving around doing other things at the same time. So don't blame you if you want to keep it off either. Without further ado, I think we should just go ahead and get into this. I'm going to go ahead and share my screen, and please feel free to, like I said, ask questions in the chat. I got to figure out which screen this is because of the new computer situation. This is what you're looking at here is my outline for what I had planned to talk about today. Like I said, we're going to start out talking about a little bit of math stuff on the MCAT from the jump here. If this is boring, or if you all feel like all of you know this, then please feel free to usher me along through this, because we do have a ton of stuff to get through, and doubtful that we'll get through every single thing today. Starting out, math on the MCAT, one of the things that I think is, it sounds trite, but is super useful to just be able to do, is to interconvert between the different prefixes that come before all of your major unit quantities. So, like millimeters, meters, kilometers, etc. I figured we could talk about that for just a brief moment while also talking about how to use numbers in scientific notation. And I'm going to blow through a lot of this too. The pace is going to be relatively fast, so some of you might want to rewatch it if you're having a really hard time, or like I said, you're welcome to ask questions. So anytime you end up with any sort of decimals at all on this test, I recommend putting them into scientific notation. And by scientific notation, I don't necessarily mean that you just have to have a number in the ones place and the coefficient and then like some power of 10. Like for instance, if we were to say that you have 4.9 times 10 to the, I don't know, let's say 4.9 times 10 to the negative 5. And we have to use that number for some math problem on the MCAT. Let's say that the test is asking us to take the square root of this, for instance. This at a glance is a really difficult problem whenever you just have the numbers 4.9 times 10 to the negative 5. However, you can make this a lot easier on yourself just by moving this decimal around a little bit to manipulate the scientific notation. So you're welcome to speak up if you have a recommendation of how to go about doing that, or I can just talk about how I would say to do it here. So nobody has anything. So I would say 4.9 times 10 to the negative 5. In order to get the square root of that, you can recognize that 4.9 can be turned into a perfect square just by moving that decimal over. So I'd go ahead and just make this coefficient one number larger. And then at this point, we're multiplying it by 10 to the, instead of negative 5, now it's 10 to the negative 6, because, we made the coefficient larger. So we need to make the scientific notation number smaller. And now all we have to do is take the square root of each of these things independently. And so if you're taking the square root of 49, that just ends up being 7. Square root of 10 to the negative 6, well, square root of any number in scientific notation, really all you have to do is divide the exponent by 2. So in this case, we'd end up with 7 times 10 to the negative 3, because fundamentally what you're doing whenever you take a square root of a number is raising that number to the power of 1/2. So similarly, if you needed to take the cube root of a number, you can raise it to the power of 1/3. If you need to take the quadratic root, power of 1/4, etc. And so whenever I say scientific notation, I don't necessarily always mean just one number in the ones place and then times 10 to the power of something. You can make the coefficient for your scientific notation as big or as small as you need to, just based on whatever is going to make that problem easy for you to do. So for instance, like if you had 10 times 10 to the something, you could make that 1 times 10 to the something. That's fantastic. Or you can make it 100 times 10 to the something, right? So it's not like you don't always have to just have it. This is just something that I see all the time. You don't just have to have one number here. I've got a few questions here that we can just run through really quickly. So first one is, how many nanometers are in 1 meter? And so if you don't already know these prefixes, I just recommend having them memorized going into the test. So if you start at 1 meter, that's sort of your base unit. And if you go out in either direction, you end up with deca, if you go one place to the right, or deci if you go one place to the left. And that just continues, just recommend memorizing those going in. So nano 10 is the prefix for 10 to the power of -9. And so if we say how many nanometers are in 1 meter, well, if we have 10 to the -9 nanometer, or 10 to the -9 meters is 1 nanometer, then that means that there's a lot of nanometers in a meter, right? So we end up with 10 to the 9 nanometers is just equal to 1 meter. And I know this is probably relatively simple for a lot of you, but I just want to touch on it. Next one here says, how many micrometers are in 1 picometer? Well, one thing you might notice here is that micrometers are bigger than picometers as a unit, right? So a micrometer is 10 to the -6 meters, and a picometer is 10 to the -12 meters. And so what we could do here is just turn our micrometer into our base unit. So if we say how many picometers are in 1 micrometer, then you find that the difference here is 10 to the 6, or 10 to the -6. So what we would say is, we could also say how many, we could say like 10 to the -6 meters is equal to X times number of picometers. And you could just at that point solve for X. Right. So what we end up with is that there are 10 to the -6 micrometers in 10 to the -6. Yeah, 10 to the -6 micrometers in 1 picometer. I thought I said it wrong for a second. And then last one that I'm going to make you do here is how many centigrams are in 17 gigagrams. I just picked 17 just to throw some arbitrary coefficient out there. So in this case, centigrams, centi is the prefix that says 10 to the power of -2. So you have 10 to the -2 grams in a centigram, or 10 to the 2 centigrams in a gram. And then gigagrams, giga, is just the prefix for like billion, or 10 to the 9. And so we would just multiply that 10 to the 2 times 10 to the 9 times 17 to get the number of centigrams that go into 17 gigagrams. So we'd say like 10 to the 2 times 10 to the 9, and then don't forget about that 17. So what you end up with here is 17 times 10 to the 11, and we're going to leave that and not change it to 1.7 times 10 to the whatever times 10 to the, I guess it'd be 12, because we want to be comfortable not just having one number in the coefficient place. I know I'm stressing that a lot, but it actually does end up being helpful if you don't have that compulsion to do that whenever you're working through these problems. It's just an extra step that ends up being not only unnecessary, but it can actually mess you up on some problems. I could actually come up with an example of one, but I'm going to stay relatively focused on this now because I do have a ton of problems for us to go through here. And then the last one of these is, what is the density of water? So does anybody know off of the top of their head what the density of water is? You're welcome to type in the chat. Or you can, if you want, vote on it here in this poll. I just reset it. So density of water, A, B, C, or D? All right, so we have 3 people who have voted out of the like 13 people in here. Oh, nice. Okay, getting some more votes. All right. Wisdom of crowds so far not prevailing here necessarily. We do have a few people who I think are on the right track. I give it a few more seconds. Okay, cool. So it looks like the majority of you voted for B, 1 kilogram per meter cubed. So what you're doing here is that you've memorized that the density of water is 1, which is true if your units behind that 1 are correct. But whenever you're thinking about the density of water as being 1, what you have memorized here is that, we'll say like rho of water is 1 gram per centimeter cubed. That's the same as saying 1 gram per milliliter. However, that is not the same as saying 1 kilogram per meter cubed, right? Because kilograms are different than grams and meters cubed are different than centimeters cubed. So the way that I would recommend figuring this out is actually coming up with a picture just to look at, just to make sure that you're on the right track here. So the picture that I would tend to recommend drawing here is just think about, well, try to draw out, let's say we draw out a cubic meter here. Okay, so a cubic meter has got to be like a 3-dimensional shape. This thing is super hard to draw on since my other computer broke a minute ago. So forgive me on that. But okay, so here's our cubic meter. So we're going to say it's 1 meter tall, right, by 1 meter deep by 1 meter wide. All right. Does anybody know what the formula for volume of a cube is? You might have to think. Do what?
Oh, sorry. You
Yeah,
just
no, go for
multiply
it.
the sides together.
Yeah. So volume of a cube, we'll just say like V is equal to length times width times height. You may have thought that you had to forget about that formula in like 6th grade at some point, but no, it's coming back here. The MCAT is truly comprehensive. Just kind of kidding. But so if we multiply length times width times height here, we find that is in fact 1 cubic meter. But if we want to think about how many cubic centimeters go into a cubic meter, we need to change each of these individual sides into cubic centimeters. Right, because a lot of you might be thinking, oh, well, there's 100 cubic centimeters in a cubic meter, but that's actually not true. And you can observe that whenever you change these sides. So go ahead and change the sides to how many meters are in it, or how many centimeters are in a meter. There's 10 to the 2 centimeters in a meter, right? And notice I'm writing 10 to the 2 and not 100, because if we had to write out 100 times 100 times 100, that's just kind of cumbersome. So I'm writing 10 to the 2 centimeters for all 3 of these sides. And so now what we find here, whenever we take length times width times height, we've got 10 to the 2 times 10 to the 2 times 10 to the 2, right? That's basically the same as saying 10 to the 2 to the power of 3. I don't really care which way you can do this either way. But 10 to the 2 times 10 to the 2 times 10 to the 2, well, whenever you're multiplying exponents with the same base, you can just add those exponents together. So what you find here is that this comes out to be 10 to the 6. And similarly, whenever you're raising one exponent to the power to another power, you just have to multiply those 2 exponents together. So what you end up with here is
or it could be something associated with medicine. It could be in the pharmacy or in the
okay, cool. So what we find here is that there are 10 to the 6 cubic centimeters in 1 meter. And so based on that, we can go ahead and run our conversion for this problem. I need to get some of this out of the way here. So what I would recommend, now that we're aware of how that's supposed to convert, weird that jumped over. Now that we're aware of how that's supposed to convert, we can go ahead and say, all right, well, we know that water has a density of 1 gram per centimeter cubed. And I still do problems like this, like writing out this sort of stoichiometric equation, just because I want to make sure I don't make silly mistakes. That is like one of the biggest Achilles heels for some of the smartest students that I have on this test, who end up underachieving, meaning that they don't get the 525 or whatever that they're supposed to get, is just making silly mistakes. So just be kind of careful whenever you're doing simple problems like this. So here I'd write it out, start with a thing that I know that I have, which is 1 gram per centimeter cubed, and go ahead and multiply. Well, go ahead and get the grams into kilograms would be the first thing I do. So I'd say, all right, well, how many grams are there in a kilogram, or how many kilograms are in 1 gram? You could do it either way. So I'd say 1 kilogram up here is equal to 10 to the 3 grams. And so now our grams are gone. And then we have to convert from centimeters cubed into meters cubed. So we put our 10 to the 6 centimeters cubed up here, right? Because you have to put it on the opposite side of the fraction bar if you want to get rid of it. And now the meters cubed get to live down here in the denominator, because that's where we want it to go anyway. And you can just confirm that your units are the same on each side, and then go ahead and multiply your numbers across. What you end up with here is 10 to the 6 kilograms divided by 10 to the 3 meters cubed, which, we go ahead and divide when we divide exponents, you can just subtract the exponents as long as they have the same base. So what we end up with here is 10 to the 3 kilograms per cubic meter. And so that is the density of water. So D is the correct answer for those 3 of you who voted for that. Any questions on that before we move on to the next thing? All right, cool. And this will all be recorded, like I said. So, and even though we're way behind on uploading the recordings on these, because Zoom just really loves to mess up the format of our webinars whenever there's a bunch of us entering and exiting. So that's why we're a bit behind, but we'll be caught up pretty soon. Anyway, so this next problem I want to use, this is a really good solubility problem. And so if you haven't been reviewing solubility recently, or if you're just getting started on MCAT prep, you might have no idea how to go about this problem. The main reason I want to emphasize this problem right now in the context of this math on the MCAT discussion is more to talk about how to round numbers effectively on the MCAT to make your life a lot easier than it is to talk about solubility specifically. So for that reason, I've gone ahead and included definitions for molar solubility and for what a saturated solution is and for equilibrium. So I'm going to talk about each of those briefly, but I don't want you to get too caught up in the weeds. The point here is thinking about how to do math on the MCAT. So this problem says iron 3 hydroxide has a molar solubility of 8.99 times 10 to the, this is supposed to say negative 10, times 10 to the negative 10. And then it goes on to say, what is the solubility constant, KSP, for iron 3 hydroxide? So the definition of molar solubility that we have written down over here on the right is that it's the maximum number of moles of solute that forms a saturated solution when dissolved in 1 liter of solvent. Okay, so another way to put that is that molar solubility has to be in units of molarity, right? Because it's got moles of solute per liters of solvent, and it's just the most of that solute that we can put in. Another way to think about a saturated solution is it's a solution whose solubility reaction has reached equilibrium, meaning the low point on that Gibbs free energy graph. I think we talked about that a little bit 2 weeks ago whenever I was talking about acids and bases. We will at some point circle back to talk about solubility in and of itself, but I just want to kind of briefly mention it here to give you context. So whenever we are setting up our molar solubility problem, we need to think about this number 8.99 times 10 to the negative 10. We're going to end up using that a lot. And that's the number of moles of iron 3 hydroxide that go into 1 liter. And so if we think about the reaction that we're looking at here, we've got iron 3 hydroxide as a solid, and that is dissolving. We'll go ahead and put it at equilibrium into iron, which is aqueous here, plus 3 hydroxide molecules for every iron and for every molecule of iron 3 hydroxide that goes into solution. And those are also aqueous. And the problem is asking us to solve for the KSP, right? So that's the same as the equilibrium constant. When you set up an equilibrium constant equation, you have to put products over reactants. So we have KSP is equal to the concentration of iron, 3 plus, times the concentration of OH minus over here. And we have to raise the OH minus to the power of 3 because there's 3 of those per every 1 mole of iron 3 hydroxide that goes in. And then our denominator here just goes to 1 because all we have over there is pure solid, and pure solids and pure liquids don't go into the equilibrium constant expression because it's kind of complicated, and I'd be happy to talk about this another time, but pure solids and pure liquids are technically not in the phase in which the reaction is actually happening. The reaction's occurring within aqueous solution, and that aqueous solution surrounds the border of the pure solid itself. But the pure solid isn't accessible by the things dissolved in the aqueous solution because at the heart of that solid, all that is surrounding any given molecule of solid or any given atom of solid is just solid itself. And so that it's not a player in the reaction for that reason. So just in case any of you have ever wondered why that's the case, these are the things that I waste my time on whenever I'm just sitting around by myself.
Do you mind if I chime in real quick?
Yeah, go for it.
Yeah, so for solids and liquids, it makes sense not to put them into the equation because if something's a pure substance, its concentration will just be 1 or 100, right? 100%.
Mm-hmm. Yeah.
So.
Yeah, for sure. So, okay, so we have these concentrations of iron and hydroxide here, and then obviously we have hydroxide raised to the power of 3, but we don't have any number that tells us what either of those is in solution at the time. However, what we do know is the number of moles of iron 3 hydroxide that went in. And so we just have to look at our mole to mole ratios to determine how to use this molar solubility number that we were given. And again, verging on diving too deep into molar solubility and to solubility in general right now. But what I would recommend in this case is thinking about, okay, well, our 8.99 times 10 to the negative 10 is going to be equal to this value of X. And then we can say how many, we go ahead and just give X because it's an easy variable to write out. And so that's moles of iron 3 hydroxide that go in. And so we want to think about, okay, well, per mole of iron 3 hydroxide that goes into solution, how many moles of iron are in solution? You can see that they're in a 1-to-1 mole-to-mole ratio in the reaction equation. And so we would say, well, then that tells us that this iron here is just equal to X. And then we want to think about the relationship between that and hydroxide as well. So how many moles of hydroxide go in per mole of iron 3 hydroxide that gets dissolved? At that point, it's 3, right? So we'd say, well, okay, that means that that is 3X. And don't forget, all we're doing is substituting in the things that are in the brackets. You can't forget or should not forget to bring along this exponent as well. So we've got X times 3X to the power of 3 in this case. And so then what we do, if we want to go ahead and continue writing this out, is we can say, all right, well, X over here, we'll just leave that alone for a second, times 3X to the power of 3. You have to just, when you distribute that 3 through, you have to raise everything in those brackets to the power of 3. And so, yeah, we end up with another X to the 3. That's great. But the thing where most people mess up here is they go ahead and say, okay, well, that's either 3, or the most commonly chosen wrong answer here, I would say, is 9, right? Because they see 3 times 3 is 9. But here, actually, we have to cube 3. And so it's 3 times 3 is 9, times 3 more is 27 in this case. And so what we end up with is, that's terrible handwriting, but what we end up with is 27x to the power of 4. Now, the whole point of doing this on our math on the MCAT discussion is to talk about how to handle this situation, because now when we sub our 8.99 times 10 to the negative 9 in for X, that is kind of nightmarish, right? We end up with, we need to raise it to the power of 4, 8.99 times 10 to the negative 10. I think I said 9 a second ago, times 10 to the negative 10 raised to the power of 4. That's going to suck some, right? So what a lot of people will do is have the intuition to say, well, okay, well, I can just round that 8.99 up to 9. And that works. That's, I mean, it's better than what you had to begin with, but you still are faced with this issue where you have to raise 9 to the power of 4. And if you're really, really, really mathematically inclined, then you could maybe square 81, but like, I don't know, that just seems kind of fraught to me. So what I would recommend doing here is understanding that whenever you have an exponent as big as 10 to the negative 10, or frankly, as small as 10 to the negative 10, that coefficient matters very little in the grand scheme of things. And so, especially because 9 is so close to 10, I would recommend just going ahead and rounding this 8.99 all the way up to 10 rather than rounding it to 9. Don't stop at 9. Just go ahead and round it to 10. So then what you end up with is 10 to the power of negative 10. And you can simplify that down even further just to make your life even easier to 10 to the power of negative 9, right? So then what I would end up with on this problem, if I were doing it on a test, would be 10 to the power of negative 9 raised to the power of 4. And that is much easier because if you remember, whenever you raise one exponent to another exponent, all you have to do is multiply that exponent through. So what you end up with here is 27 times 10 to the negative 36. It's just a much easier number to work with. The reason I picked the 8.99, I made that number up. I didn't technically make it up, but that value is 8.99 times, I think it's 10 to the 9, is the value for the constant in Coulomb's law, the electrostatic force and electric potential energy, that equation. You've got K times Q divided by R squared. And so I like using this as the example here because in all of your electrostatic force or electric potential energy problems that you may have to do on the test, go ahead and just make that constant 10 to the 10. Right? It's just so much easier to work with than 8.99 times stuff, because that's just kind of complicated and going to waste your time on the MCAT. But also, anytime you round, remember the direction in which you rounded, right? Like if you're going to do this multiplication and you want to round 8.99 up to 10, just remember that you rounded up so that if you're stuck between two answer choices at the end, once you've done all the math, that you can remember that your answer is a little bit bigger than it maybe should be. And so if you're stuck between two after having rounded up predominantly, then make sure you pick the smaller answer choice. Anyway, moving on from that, does anybody have any questions on that before we move to the next thing here? Keep in mind, we have a ton of problems to do. Not to discourage questions either, but okay. So next thing I have here is to talk about, this is maybe one of the most important things I'll say today, is thinking about how to understand or how to learn the equations on the MCAT. I think most people here are already tutoring students with us. But if you're not, then you may have even seen the equation sheet that I have floating around out there in MCAT space. I made it when I was studying the MCAT. Basically, I typed up every equation on the MCAT, put a few bullet points that mattered to me personally for those equations. And then I read that like every day for like a month or two when I was studying for the test. It's kind of a brute force method. My equation sheet's not the best one ever. It is typed, which is kind of nice, but it had bullets in it that were specific to me at the time. So I always recommend to people make one that's specific to you as you're going through this, to make your notes, and then do read through it like every day, quiz yourself on it. But the point of all of that isn't for you to just memorize by heart every variable of every equation, because you can manipulate these equations and you can regenerate them if you truly understand what's going on as well. What is really more helpful than that is to understand the units of those equations, which we'll talk about here in a minute. But my point of emphasis here is to understand the correlations between variables in these equations. It's rare on the MCAT for them to just ask you to take these numbers and plug them into this equation and get this output, and that's your answer. That is, I mean, it'll happen occasionally, but that is far and away way less common than them asking you to understand the correlation between two variables. They can do that because, one, it allows them to assess your knowledge without having to account for the probability of random error in math. Because what the AAMC's job here is fundamentally to get an assessment of your ability to succeed in medical school, and you're not going to be doing like 10 to the 6 to the power of 4 very much in medical school. Like, it's just not that super useful. So they want to make it easier for them to test your understanding. And the way that they do that is asking you questions like what I have right here in number 6, which is testing your ability to understand the correlations between these variables. So for instance, in this question, I say fluid A is moving through a pipe with perfectly laminar flow. What happens to the fluid's velocity if we, and then let's just talk about each of these. So I've got the poll running right now. What do you think happens to the fluid's velocity if we double the cross-sectional area of the pipe? Go ahead and pick A if you think that the fluid's velocity is going to increase by a factor of 2. Pick B if you think it's going to decrease by a factor of 2. Pick C if it's going to increase by a factor of 4, and D if it's going to decrease by a factor of 4. Okay, so you got one vote. I think that was for increase by a factor of 4, right? So let's go ahead and think through this. Well, first thing we might want to figure out is what equation governs this law, or what equation governs this situation. That equation in this case it's called the continuity equation. You'll probably have seen it most frequently written out as A1 times V1 equals A2 times V2, where A and V are cross-sectional area and velocity, respectively. This equation is really a simpler version of what I call the conservation of flow equation in a continuous fluid. So I just say like flow 1 equals flow 2. And the reason for that is because flow, well, if you are really familiar with the units on this test, you'll be aware that flow is technically defined as volume of fluid moving past a certain space in the pipe per unit time. And so flow is really volume divided by time, or you could say like meters cubed divided by seconds. So meters cubed divided by seconds on both sides. And you can see that that actually works out with the units of area times velocity, right? Because area is in meters squared times velocity in meters per second. So what both sides end up equaling is meters cubed per second. We'll talk more about units here in a minute. But and so what we can see here is that if we double the cross-sectional area of the pipe, let's say that A2 is twice as big, twice A1, right? What that shows you is that the velocity of the fluid through that pipe, when we double the cross-sectional area, in order for flow to remain constant, the velocity of fluid in that section of pipe would have to be cut in half. And so I don't remember which one was which one that was. I think I said it was B, but that would be the case for that. The next one here says what happens to the velocity of the fluid if we double the radius of the pipe. Okay, so think about it, and again, in the context of this equation, what is the relationship between velocity and radius? So we'll say A says that the velocity is going to increase by a factor of 2, B decrease by a factor of 2, C increase by a factor of 4, D decrease by a factor of 4. Go ahead and vote whenever you want, if you want to. I do recommend voting so that you can get a sense of what's going on here. Okay, nice. So we got 4 people voted, 3 of whom voted for D, which was decreased by a factor of 4. Just giving people a second to think about it. And if you're not sure whenever you run into this sort of thing on the MCAT, you do have time on this test to just test this for yourself. what I would recommend here is say, well, okay, I know radius is factored into area, right? Like area is going to be equal to pi r squared. Okay, and so radius here times velocity 1 is going to be, equal to, again, pi r, we could call it r2 squared times velocity 2. And so you can see that if you double the radius from 1 to 2, from side 1 to side 2, you could put in some random numbers to make this work out for yourself. Your pi's can cancel each other out, so you don't have to worry about those at all anymore. And then you can say, okay, well, r1 squared times v1 is proportionate to r2 squared times v2. And then you can just bake up some numbers. So you say like, okay, well, let's just say that r1 is 1 and r2 is 2, right? Because we doubled it. And so then what you'll find is, okay, well, 1 times v1 is proportionate to 2 squared, which is 4 times v2. And so then what you'll find is, in order to make this equation work, v1 has to be 4 times greater than v2. And so D would have been correct, which is what the 75% of you who voted said. All right, cool. Next one here says, what happens if you double the flow rate of fluid A? Basically what that's saying is, remember I said flow times flow is what this equation is. So if we double the flow on one side, right, then, well, it's saying what happens to velocity. So if we double flow on one side and we don't affect cross-sectional area on the other side, then that tells you velocity has to double as well, right? So I just wanted to go ahead and give you that one so I don't waste everybody's time doing questions you all already know how to do. And then the last one I put here said B and C. So in this case, we're saying we double the radius and we double the flow. Well, whenever we double the radius, we just showed that doubling the radius quadrupled the cross-sectional area of the pipe, all right, which would decrease velocity by a factor of what? Does anybody know? It decreased velocity by a factor of 4. Okay. And so if we double the radius, velocity would decrease by a factor of 4. But then we also double the flow rate, which means that if we aren't changing the cross-sectional area further, then the velocity from having decreased by that factor of 4 would now double. And so what your overall result here would be for option D, or I guess like sub-question D, would be that velocity would decrease by a factor of 2, or you could say decrease 50% or whatever, be cut in half. So anyway, just the point here is to pay attention to, as you're going through these questions on the MCAT, or as you're studying the equations, more importantly, to pay more attention to the correlations between variables than you pay to memorizing the entire equation. Because like I said, you're rarely going to be called upon to use an entire equation for a problem. It's usually a subsection of that equation based on how variables correlate with one another. The next thing I want to talk about that is super pertinent to that is how to go about creating a graph of an equation whenever given just the equation, or given just a correlation between two variables, or how to create an equation given a graph, or something like an equation given a graph. So this one says create a graph showing what happens to velocity when we change each of the variables above. Showing what happens to velocity when we change each of the variables above. Crazy. I don't want to do that. That's going to take too long. We're not doing that. We will do a subcomponent of that. So we're going to say, let's go ahead and create a graph to show what happens whenever it asks for velocity. So what happens to velocity whenever we change, let's say, radius? We'll put that on the graph. So first of all, the variable we're concerned with here is velocity, right? So the graph is showing what happens to velocity. What does that tell you about the axes of this graph? Does anybody have any thoughts on that? I know you're welcome to speak up, but I know it's kind of annoying to have to just like talk out loud in a meeting with a lot of people.
Velocity is going to be on the y-axis.
Yeah, perfect. Okay, thank you. That's exactly what I was looking for. Yeah, so whenever the variable that we're concerned about, or the variable we're looking at, is the dependent variable, and that's just by convention placed on the y-axis. So that's not to say it can't ever be on the x-axis, but just conventionally you would expect the dependent variable to show up on the y-axis. That's a super useful hack to moving through MCAT passages. The first thing I do whenever I am going through a chem phys passage or a biochem passage is that I will, before I even start reading, I just look at all the pictures. And the reason I do that is because I want to know what in this passage is super important before I start actually reading the thing. Because if something, if they're giving me all these 15 million transcription factors, like they sometimes do in the biochem section, for instance, I don't want to pay attention to every single one of those as I'm going through the passage if only 3 of them are going to be relevant. And so I'll first look at all the graphs that they give us and see, okay, well, this thing has one dependent variable that's like mRNA expression. And I know that's biochem, but in this case, one dependent variable that is velocity. And then it puts on the x-axis 16 dependent variables, right? And sometimes it'll make these the different dashed lines or diamond versus square versus circle lines on the graph. But everything that's not your y-axis, whether it's a different format of the line or if it's the x-axis, is a different dependent variable. And so I'll just note those before I go through the passage. And then when those pop up when I'm reading the passage, I'm like, okay, well, that means that Wnt 5 is going to be important because it was on the x-axis, but I don't know, Sonic Hedgehog is not, because it's not one of the variables in the experiment. They just happened to use this in both the control and the experimental group because it was necessary for some reason. So that's one of the things that I do just right off the bat going through a passage. So in this case, thank you, Roop, for the answer on this. Velocity is on the y-axis, and in this case, we are looking at, I think I said radius. We're going to go ahead and say radius is our variable on the x-axis. And so given what you know about the relationship between radius and velocity, what does this graph look like? Remember, the equation was a1 v1 equals a2 v2. Okay. So, and we could simplify that down to be, pi r1 squared times v1 equals all of this over here, right? So what you can see is that as radius increases, velocity has to decrease. But as radius increases, the effect it has is more significant than that of velocity, right? So as radius increases, velocity is going to drop off exponentially in this graph. Okay, so while radius is small, velocity is big. And while radius is, as soon as radius becomes big, velocity gets really small. And so this graph is going to look like this. Tried to do it. Let's say this graph is going to look something like this. How is this graph different than the graph between velocity and, let's say, cross-sectional area? Because I feel like that could be somewhat challenging for people here.
Is it just linear? It would just be a linear decreasing going down.
So, well, velocity and cross-sectional area are still inversely related to each. Oh, so you're saying, you said linear going down like this?
Yeah, instead of, like that, yeah.
Okay, so you can run a quick test on this to see whether that's true. The quick test, I made this up one day when I was teaching. I know I didn't like invent it. I'm sure plenty of other people thought of this. But one quick test to see whether an equation is linear or not is to set the variables that you're interested in, the variables that correlate, on opposite sides of the equal sign, and then compare their exponents. If their exponents are the same and they're on opposite sides of the equal sign, then the equation is linear. If they're not, then the equation is not linear. And so in this case, we've got cross-sectional area and velocity. And we're just going to say it's equal to constant over here so that we can, show the variation. And so whenever we move one of these to the other side, let's say we go ahead and move velocity, or we'll go ahead and move cross-sectional area to the other side. Then what we end up with is velocity, and the implied exponent here is 1, divided by, or time is equal to constant times 1 over 1 over cross-sectional area. And so 1 over anything is that thing raised to the power of -1, right? So it'd be like constant times area to the -1. And so in this case, those exponents are not the same. So what that tells us is that this is not linear, because the exponents are not the same when placed on opposite sides of the equal sign. So this equation has to have a curve of some sort to it. And what you can see based on, again, that equation right there is that these two are inversely correlated. As velocity gets big, cross-sectional area gets small, and vice versa. Well, technically it's as cross-sectional area gets small, velocity gets big, because cross-sectional area is the thing that we're saying is independent. And so this graph is going to look almost just like the red one that I drew first. It's just going to be less dramatic because it's a 1 to -1 relationship instead of like a 1 to -2 relationship between the exponents. So this graph here between, we'll say, like, I guess radius was the red one. So we'll go ahead and say the green one is going to be area. So this graph is just going to be like less dramatic.
Yeah, you could also think about what number area cannot be. Like what
I
number
agree with this.
not, yeah, what number can be denominator not be. I mean, you can always just also plug in values and you can see that as the velocity value goes up, the area value just gets smaller and smaller and smaller. Like if you had a velocity of 100, the area would be, going to be like 1/100.
Right.
So you're never, like, the axes will just become asymptotes and you're never going to actually, touch them. You'll just infinitely be approaching them. But this is something that they like to ask a lot on this test because it's very easy for people to, think that it's just going to be a linear line going down. So I've seen this asked, many times. So
yeah, it's definitely, this will be on your test. I mean, I don't know if it'll be area and velocity or if it'll be, any other number of things that could be on this.
Inverse relationship.
Yeah, like pressure and volume is it's another one that comes up all the time on this. And so I really appreciate the linear, the even though your answer is wrong, that's like the best answer you could have given for the sake of this discussion here. So thank you for that. I promise I'm not pre-prompting people. But no, and what Shane was just saying about the about testing values or about seeing where it should cross the axes, that's absolutely correct. I do this all the time whenever I'm doing these problems, just to triple check myself. Is I'll just think about, well, okay, can one of these variables be 0? And the answer to the equation still be some non-zero integer that was constant throughout, right? Like when we said area times velocity equals constant. If we say, let's say constant is 100 or something, as velocity goes to 0, as velocity approaches 0, area has to get enormous in order to keep that net value from changing from the constant of 100 to 0, because the constant has to be constant. So just wanted to reiterate what Shane was saying there, because that's a really good tip, and it's a better tip than what I was saying. I like mine in scenarios where you need to come up with sort of the inverse of this, where you're given an equation and asked to pick out a graph for it, or sorry, when you're given a graph and asked to pick out an equation as well. So you can do this in both directions. All right, so anyway, that's just things to think about. It's useful to plug in numbers again, like Shane said, and like I said earlier, whenever you're not sure what else to do, just plug in a couple simple numbers, see what happens when it's 1, when it's 2, when it's 0.5, and then go from there. All right, so moving on from this is another part that people really struggle with. This is where calculus comes in on the MCAT. Even though they explicitly state that they won't test calculus, they still kind of do. They just do it like incognito calculus. And so here what I'm talking about is looking at the slope of lines and the area under curves of lines. So in this scenario, we want to come up with, well, I put what is the equation for this graph. That would be insane to try to come up with that. More importantly, I want to say, so in this graph, we've got velocity on the y-axis and time on the x-axis. So I want to think about how you would go about finding acceleration in this graph. Does anybody have an opinion just right off the bat, or any comments that they would like to say, or a guess that they want to throw out? Because this is obviously this is not a simple graph right here. And you don't have to give me a number off the top of your head. I mean, that would be pretty impressive if you were able to integrate that whole thing, or I guess to differentiate the whole thing. All right, so the way that you go about finding the acceleration in this case is, well, the way that I recommend doing this is whenever you're given, say you're given things that you're not already familiar with, you may be familiar with the fact that the slope of velocity versus time graph is acceleration. But let's say this is in some units that you haven't seen before, or that you forgot about, or something like that. We know that the thing that we're looking for is acceleration, and you may know that acceleration is in meters per second squared. And you were also given your y-axis is velocity in meters per second, and your x-axis is in time. So if you had no other means of determining, for instance, if you hadn't memorized that slope of the velocity versus time graph is acceleration, what you could do is say, like, okay, well, how do I get acceleration given the variables of the two axes that I'm given? Right? So here we can see, well, meters per second and seconds. It's not super difficult to see how we get acceleration out of that. All we have to do is divide velocity, divide our y-axis by our x-axis, and we end up with acceleration meters per second squared. And so anytime you take basically what I said here when I said divide velocity by time is divide y-axis, right? Y-axis by x-axis. Y divided by x, same as you probably have heard it a million times over as rise over run, which is slope, right? So that's that's how you go about finding that. Similarly, let's think about how we would find, let's say displacement. That's what I'd written down here. So let's think about displacement in this graph. Where does displacement come in? Well, use the exact same approach, right? So here we have our axes again, our velocity and time. And so in order to get displacement, which is in units of meters, what we need to do is multiply our y-axis by our x-axis. So whenever you're trying to find something that, that is, well, the slope of the graph is going to be the y-axis divided by the x because it's rise over run. But if you're trying to find a different unit going sort of the opposite direction, you just need to multiply your y-axis by your x-axis to find what that is. And what we're doing here is finding what's called the area under the curve, which is the integral of the equation if you were to be doing calculus on this test. But it's usually always a lot simpler than that on the MCAT. So in this case, we just say, like y-axis, y times x in this case is equal to meters per second times seconds, which is equal to meters, and that's displacement. So that would be the same as finding the area under this curve. I have seen it come up on the MCAT before where they don't give you any kind of equation for this and they just throw a graph out, but they'll put some really faint, kind of poorly done graph paper behind it. And so they'll have you, and that's why I wrote out the, the numbers here, so they could force you to do something like this and to think about like how much of each of these squares is colored in here. And so you could also literally just like count the boxes underneath this and then come up with fractions for the partial boxes, like this small one over here on the far left bottom would be like a fraction of a box. This is maybe like half of a box. Here's a full box, half of a box, etc. And you literally just count those up to find the displacement over the course of this journey that this person went on. We can assume that is a person in a car or something. Any questions on that? Because that is something that people struggle with a lot, but I also don't want to belabor the point if all of you here have a good grasp on that. Okay, cool. We'll come back to this here in a little bit. I've got a problem later on that will test your understanding of all of this. Okay, cool. So that is it for my math on the MCAT section, except for the units. So if any of you have had any meetings with me personally, you will have heard me just beat this into the ground. I'm a huge fan of the units on the MCAT. So first thing that I want to think about here, though, is how to go about, I want to kind of elaborate on what I mentioned earlier, how to go about solving a chem phys problem, specifically a physics problem that you're really not sure how to approach. So like where to start. Well, first of all, most of these are associated with passages, by definition, like a quarter or like 3/4 of the questions on the section are associated with passages. And those passages are usually going to have a lot of units throughout them, both in the graphs as well as embedded in the passage. The question stem probably does, the answer choices probably do. So the first thing I recommend whenever solving a problem you're not really sure how to go about doing is just look at the units and see if you can make something up. That is, it works really, really well, surprisingly. And if you get good at this section gets so easy. When I was studying for the MCAT, I was doing better on biochem than chem phys for quite a while because I was a bio major and had frankly wasted too much time in undergrad studying for my bio classes. So I was well positioned for those and didn't have much of a physical sciences background. But as I got deeper into this and really got a deep understanding of the units and how everything interconnects, it informed me on the big picture perspective you can take on this a lot more deeply than I could have otherwise guessed. But two, and this is more relevant for you right now, I don't know how into the philosophy of science all of you are, but I know you're into getting a really good score on the MCAT. So the second thing it did for me was it made chem phys legitimately become easier than biochem. By the end of studying for the MCAT, I was finishing the chem phys section usually with like 45 minutes left on it, just because I got super fast at going through these passages and finagling the units is like one of the most useful things, both to solve problems you're not sure how to approach otherwise, but also to go back and check your work. So strong emphasis on this. Understand base units on this test. So there's only like a handful of base units, first of all. By base units, I mean things that don't break down into other things. So like joules, for instance, not a base unit, right? Because you can break joules down into newtons times meters, and you can break newtons down further as well. So if you think about what are base units, well, one of them is, and you can all throw some out if you want, but one of them would be like mass, for instance, or in the case of mass, it's kilograms, is our base unit that we're looking at. Another one is displacement, which is going to be in meters, right? Another one is time, which is in seconds, okay? Those are just a handful of them. You also have charge, which is in coulombs, resistivity, which is a totally different thing. We can talk about a different time. I think that's all of them. Shane, do you have any others on the base unit, like things that don't break down into other things?
Not really.
Yeah, I don't think there are. There's like 5. It's super simple. But then all these other units that you have to be aware of, which can get relatively complicated, are just built up from there. And so what I recommend doing, and I put a couple of these in your student folders. If you find that you don't have these in your student folder, that means that you signed up to work with us before I made these. So just let me know and I can drop them in. It's not a big deal. I just have a few example questions on this one. I think I've got like 20 of these inside the folder. So you're welcome to check these out at any point. But the assignment here is just to solve for X in all of these. And some of these aren't necessarily useful for working it out on the MCAT. You're not going to run into a question like this on the MCAT, but it's an exercise that quizzes you on your understanding of these. You can also just make these up on your own. Like I just made all of these up one day and just drop them in your folders to give you extra exercises to do. So this first one is a relatively simple example, but I give you work equals force times X. Okay, and so if you know the equation work equals force times distance, then you can go ahead and solve X as meters, and that's distance or displacement, I guess I should say. But if you didn't, let's say you didn't know that equation, there are other ways of doing this. And what this is going to do is help you understand that you don't necessarily have to have everything memorized, or that it is good to have things memorized here. But what's more important is to have a deep understanding, because then you can regenerate stuff when you forget it. So in the case of work equals force times X, we could go ahead and say, well, work divided by force is X, right? Since our assignment is to solve for X. And then if we still don't know that equation, we can go and say, well, all right, work is in units of joules, because work and energy are the same thing, and force is in units of newtons. And so if I put newtons, and so then I also know that joules breaks down into newtons times meters, right? And so then if I put newton meters on the numerator and newtons in the denominator, then I end up with meters. And so I know X is meters. This next one is a little bit more difficult, but we can go ahead and work through it. So X times meters cubed equals volts times coulombs. And most of you are probably like, I don't know what we're supposed to do here. But and a lot of the time, I found a lot of people have a hard time with the electrostatic units. People are usually pretty good with velocity, acceleration, force, but then fall apart whenever it comes to electrostatics. So I recommend looking at all of the Coulomb's law, and all of the derivative equations that come from it. And I don't mean B equals IR on this. I mean that electrostatic force is equal to this constant K times Q1 times Q2 divided by R squared. Understanding this equation and all the derivatives from it's going to help you a ton. So what I can tell you is from this, that what volts are is in terms of units is joules per coulomb. Another way of thinking about the voltage of a circuit is that is the number of joules 1 coulomb of charge will carry with it whenever it leaves a battery. For instance, if it's a 12-volt battery, then 1 coulomb of charge from that battery carries 12 joules of energy. It has the capacity to do 12 joules worth of work. All right, so if we say that volts is in joules per coulomb, and we're multiplying this by coulombs, well, that's nice. Okay, so it ends up being in joules. So now we have X times meters cubed equals joules. All right, well, many of you may not have seen meters cubed go into joules before, but I promise you have. So what I'm going to do is pretend I already know what this equation would be, and think about, okay, well, we can break down our joules into newtons times meters. And if we're dividing that by meters cubed, then what we end up with, well, we can get rid of our meters from the numerator, and we can also lose one of our 3 exponents on the meters in the denominator. And what we end up with here is newtons per meter squared. Now, if this still doesn't mean anything to you, then, well, 1, you need to work on your units. But 2, you can also think about, all right, well, I know that these are units for things that I'm aware of, right? Like you may understand already that newtons are units of force, right? So you could say, all right, well, force is in my numerator, and meters squared, we've already talked about that like 7 times today. So meters squared are the units for area. And so force divided by area. And now at this point, you may be familiar with the fact that force divided by area is equivalent to pressure. And if we go back, and so that tells you that the SI units of pressure are newtons per meter squared. Another way of thinking about that, newtons per meter squared are equal to pascals. But I wouldn't call pascals a fundamental unit, right? When we were talking about mass, time, can't think of all of them right now, mass, time, charge, displacement. I wouldn't call pascals that because it breaks down into newtons per meter squared, right? So that's just how to go about doing this. Let's go ahead and do this next one. So we've got pressure times velocity equals x. I kind of do want to give you guys answer choices on this, but the reason I'm not going to do that right now is just because you could end up so far off in the weeds on these, and we don't have time for every single person to talk about the stuff that they're going to do. So I'm going to go ahead and just think through this one, just like I did the previous one. So in this case, we've got pressure is, again, we just talked about pressure is, so we could say newtons per meter squared, right? And we have velocity over here, which is meters divided by seconds. Okay. So any thoughts on, what that might end up being? That's kind of a weird looking one, right? Okay. So, frankly, like it's not obvious to me, and I made this up, but what I would do, so let me just go ahead and work through it. So what I would do here is say, all right, well, I know newtons times meters up there in the top is joules, right? So I go ahead and make that joules. And I know meters squared times seconds down here, the denominator still there. Okay. You can pick any fraction of these things to work with. So we can go ahead and say, well, I know that joules per second is watts, right? Or is power. Okay. And so now we've got joules per second times 1 over meters squared. I just broke my fraction up in a different way so that I could think about it differently. And so I've got, all right, well, we've got power and then basically dividing it by area, right? So power divided by area. This is a less common one on this test, but you would see it come up. For instance, if you're looking at like the brightness of a light or the loudness of a sound. Loudness of a sound, I would say, is the most common for this to come up. So what power divided by area ends up being is intensity. And so this is directly referred to in the loudness of the sound equation. Like if you want to calculate decibels of a sound, you've got decibels, which is variable beta here is equal to 10 times the log of the intensity of your sound divided by the intensity at the minimum threshold of hearing. Not going to dive into that right now. That's not within the scope of this meeting today. We talk about, it'd probably take us 40 hours to talk about everything on the MCAT, but that's again, just how you want to get to where these are all easy problems for you moving through the MCAT. So we'll go ahead and do this last one here.
Oh, can I say something really quick?
Yeah, go for it.
So something that they like to test on this test is intensity, and it's very easy to confuse intensity with energy, especially if you're talking about light or photons of light. So a lot of times, like let's say that you need a specific amount of energy to have a photon absorbed and causing an electron to go to its excited state. They might ask you, if the photon doesn't have enough energy, they might ask you, what if you increase the intensity? And that's going to be a trap answer because intensity will just kind of correlate to number of photons rather than the actual energy of the photon. So that's just something to think about.
Yeah, thank you for that. Yeah, absolutely. Intensity with reference to light, like Shane just said, refers to number of photons because photons are discrete. Photons are discrete, and the energy of a given photon is dictated by its frequency alone, frequency only. Like, and that does not mean wavelength. I talked about this in the light and optics webinar I did like a month and a half ago or so. Frequency is the only thing that matters. Wavelength is subject to change based on the refractive index of the medium that the light is traveling through. And so frequency is the only thing determining the energy of a given photon, and so that leaves just number of photons as your only variable that can be left to determine intensity here. Similarly, another way I like to think about intensity with respect to sound is the examples I always give when I'm teaching this are of a bomb going off in a frictionless environment, let's say. So if a bomb goes off in a frictionless environment, you're going to have a certain amount of energy that is released in that bomb. Nearby the bomb, really close to the bomb, the intensity is incredibly high because that energy is only spread out over a small area. The energy at the wavefront in that bomb is going to be the same both immediately right next to it and 100,000 miles away. The energy at the wavefront is unchanging, right? Because I said we're in a frictionless environment, so it doesn't dissipate at all. However, while something that was sitting immediately next to the bomb was completely obliterated, something that was 100,000 miles away won't ever even be aware that there was a bomb. And the reason for that is that even though the energy is the same, the intensity falls off with the square of the distance because we've got meters squared in the denominator, right? So if intensity is 100, 1 meter away from the bomb, then what do you think intensity is, let's say, 100 meters away from the bomb? The way to work this out, because I don't want to belabor the point too much, but the way to work this out would be to say, okay, well, we went from 1 meter to 100 meters. So we 100x'd our distance, right? But we know that intensity will decrease with the square of the distance, right? So if we've 100x'd our distance, then what that means, we have to square that number in order to find out how much intensity dropped off. So if the intensity was 100, 1 meter away, then at 100 meters away, it's going to be what, like 0.01. it's going to be 0.01 or 10 to the negative 2, right? Because it falls off 10,000x whenever distance is increased 100x. All right, cool, nice. Thank you for that, Shane, by the way.
Yeah, and intensity for light could be thought of also as correlating with brightness, just like with sound it relates to loudness. So
yeah, absolutely. I just noticed that I look totally blue in this screen right now. I think it's so I'm on my laptop and everything's messed up in my office space right now. We've got this.
You're taking silver, colloidal silver or something.
Nice. Yeah. Okay, so then in this last one here, and actually as I'm staring at this one, this is one that we've already talked about today as well. So we've got x divided by velocity equals area. So what I would recommend in this is sort of nonsensical starting out. So I'd just go ahead and isolate x on one side. So I'd say x is equal to area times velocity. Have any of you seen this ever in the last 30 minutes? Like 5 or 6 times? Well, we said that area is meters squared, right? And velocity is meters per second. And so those two multiplied by each other, meters cubed per second, or you could say volume per time. And if you were present for our continuity equation discussion, you'll find that area times velocity is what was in that continuity equation. And remember, I said that continuity equation I call it conservation of flow equation. I know it's not that, but that's what I call it, and that helps me think about it. So what this is just flow, which is volume of fluid moving per unit time. This is a really important concept to understand for cardiovascular system. I frequently will pair those two up with people. So, we will do a webinar on that at some point in the next couple of months, where we talk about cardiovascular system, fluid dynamics. Bernoulli's is really important. We might talk about that here in a second, actually. I did have a problem ready for that, and all of my conservation problems got deleted here whenever my computer crashed 20 minutes before this meeting started. But I can make these up as we go. So anyway, but that is it for the sort of finagling units component of this. Does anybody have any questions on the units before we move on to steps 2 and 3 of solving chem-phys problems that you're not really sure how to approach? Okay, cool. So like I said, first step, whenever you're not really sure what to do in chem-phys, is just mess with the unit, see if you can get an answer. It's super efficient. If you get good at it, it will also facilitate your understanding. I'm serious, like a very, very deep understanding of all of this stuff. I've been teaching MCAT for like over a decade at this point, and I still find relationships that I wasn't aware of. I don't know if that's the case for you as well, Shane, but it's pretty wild and mildly embarrassing that can happen. So what I'm telling you here is not that I'm incompetent. It's that even if you think you know it all, keep messing with it. Keep trying to find relationships that are true. For instance, you can find that the bomb thing that I was just talking about, that's not something that's in the book, I don't think, but it's something that you can just reason to be true based on your knowledge of how these units work out. Or you could also say, like, for instance, well, we were looking at a relationship between like joules and meters cubed or meters squared or something like that a second ago. If you think about what volume is, well, what meters cubed is volume, right? If you think about what pressure is, that's newtons per meter squared. We talked about that already, right? And so if you think, okay, well, pressure times volume, pressure pressure, newtons per meter squared, times volume, meters cubed, is newtons times meters, which is joules. So work equals pressure times volume, right? Or you could say pressure times volume equals constant, so long as temperature doesn't change, or so long as number of moles doesn't change, right? So this is where the ideal gas law comes from. So you can regenerate all of this stuff based on pure understanding of units alone. Anyway, I'll get off the unit soapbox now. So then the next step, if the units aren't going to work for you, because they frequently will, but they won't always. Otherwise, everybody would just get, like a 132 on Chem Phys. The next step that I go to is always conservation of energy. And the reason that I do that, well, one, just because they love to test it, but two, because joules are kind of like the common denominator between all the different categories of things you could talk about here. So like if you're thinking about how fast a car is traveling, you can very easily think about how many joules it took to get it up to that speed, or how many joules it would take to slow it down. But you could also think about charge moving through a circuit and how many joules that each charge is carrying, or how many joules the resistor is pulling from that circuit. You could also think about it in terms of like light propagating through a vacuum, or sound propagating through a medium, or radioactive decay. So joules are just the common thing. They're also super relevant for the biology section. Like we think about calories all the time in modern society, but calories and joules are interconvertibles. It's just a conversion factor there. So, like ATP burned can do a certain amount of work, can increase the volume of a balloon a certain amount per molecule of ATP that gets burned. So joules energy is the you say like the translator for all of these quantities and seemingly disparate ideas that you're going to have to deal with on this test. So conservation of energy is king. I think that of the three steps in this, units are the easiest. Conservation of energy might be the most relevant. So I'm just going to go. I lost all my conservation problems, but I can make them up as we go. So conservation of energy is fundamentally just saying that if in a process that's devoid of non-conservative forces, or a better way to say that, maybe a process for which all forces are conservative, or you could just say no friction, that the energy of the system at the beginning will be equal to the energy of the system at the end. And you will find tips, little incognito or subtle tips for you throughout the passage and throughout the question stems that tells you whether conservation is being violated or not. And if it is being violated, you frequently can find the degree to which it's being violated and use that to solve your problem. So let's say, for instance, conservation is not being violated. Frequently, they'll just say, there's no friction, or all forces are conservative, or something like that. Then really all you're dealing with here is energy one equals energy two, or energy initial equals energy final. You put it either way. But they could also tell you that maybe conservation is being violated, or to the extent that it is, they're saying that maybe a certain number of joules are dissipated as heat energy throughout this process. In that case, let's say we start with a situation, energy one, and then we end up with energy two, but they tell us that it got so X amount hotter, right? And we could just say like, well, then energy one is equal to energy two plus heat that was dissipated. And you can calculate that heat based on whatever variables they give you, whether it's specific heat or they tell you, any number of things. There's a lot of different ways to do this. So you can add your own variables to the conservation equation very, very easily, just by thinking about on which side there is greater or less energy based on what they were telling you in the passage or in the question stem. So the specific instances of conservation of energy are super, super useful to be aware of. The fundamental one that most of you will be aware of is the potential energy plus kinetic energy is equal to potential energy plus kinetic energy. Let's say 1 and 2 for each of these as well. And then the ball rolling down a hill example is probably the most common one that you'll see come up. So we'll say that that's a really squiggly hill. Say that we've got a ball sitting up here on top of the hill. You don't know what the mass of the ball is. We'll say that this hill from the valley floor is 14 meters, and this hill over here that it's going to roll up onto is, 5 meters. Okay. Your assignment here, V1 equals 0. Your assignment is to calculate V2. All right, so let's go ahead and think about how to calculate V2 from V1 equals 0. First thing that I would do here is, and maybe you just type your answers in the chat or something. I don't have a poll ready for this, and I frankly don't know what the answer is going to be because, like I said, all my conservation problems got deleted. So the way that you go about solving this is think about, well, here all we're dealing with is gravitational potential energy and kinetic energy of the ball rolling, right? So the equations for this equation, potential energy in this case, is all gravitational. So we've got mass of the ball times downward acceleration due to gravity times the height 1 in this case, plus kinetic energy, which is 1/2 times the mass of the ball times velocity of the ball at the beginning squared. And that's all going to be equal to the same stuff just at the end here. So this is the equation we come up with. I recommend before you start just plugging stuff in, see if there's some variables you can get rid of just to make the process a lot cleaner for yourself. I didn't give you the mass of the ball, but you really don't need the mass of the ball, right? You can go ahead and just get rid of that from every single component of this. I'm going to copy this. Oh, I guess I'm not. Never mind. Okay. So you can go ahead and knock out mass from each of these. You can also knock out initial velocity, right? Because I told you that it was 0. On the MCAT, they'll probably say like it's sitting at rest or it's released on a hill, or, you know, they aren't going to say initial velocity is 0, right? So you just look for things like that. And if you see it in a passage, highlight that, because that, like, if they go out of their way to tell you initial velocity is 0, you're going to use that. Like it's, I mean, not always, but, you know, because that's an extreme answer choice, but frequently you will end up using it most of the time. All right, so we can go ahead and eliminate our initial velocity variable and everything associated with it. There's still one more thing left, though, that we can eliminate here. You know, a lot of people try to solve this at this point. Technically, you can solve it where we are right now, but the point here is this is a really fast test. And so if you can solve it more efficiently, you want to go about doing that, right? So any thoughts on what other variable could be eliminated here? You're welcome to like type it in the chat, or just speak up and say it out loud if you want. Any opinions? Sometimes people will want to eliminate G. They'll be like, can we divide everything by G? The answer to that is no, because there is a G on both sides of the equation. But if you're dividing by a variable, you have to divide every added part of that equation. I don't know what you would call that technically, but you have to divide every single one of these by G. So what we would do is we'd be able to get rid of this G, but then we'd have to have that divided by G. We'd get rid of that G, but we'd have to have that divided by G. So that's not helpful in this case. We already got rid of mass, got rid of V1. So the next thing that we can get rid of here is one of the heights. And the reason that we can get rid of one of the heights is that height is a relative term. What I mean by that is, if I were to ask you, let's say I ask you how tall Mount Everest is, and maybe there's one of you who is a fanatic of like mountain climbing or watching documentaries about mountain climbing, and probably fall in the latter category, especially when it comes to Himalayas. Those are scary. But if I ask you how tall Mount Everest is and you're knowledgeable on that topic, you tell me like 29,450 feet ish. And so my question to you there is like, oh, wow. So wait, so you're telling me that if you're sitting at base camp in Everest and you look up at the peak, it's 30,000 feet above you? And no, that's just not true. Like if you went there, I mean, I'm sure it looks really cool, but it's definitely not like 30,000 feet above base camp. And what you would find, I think, is Mount Everest base camp is like 20,000 feet. So the peak is like 9,000 feet above you. Still pretty cool, but it's not 30,000. So my point here is that Mount Everest is 29,450 some feet. But what's important to note is that is the reference frame you're using here. Like Mount Everest is 29,450 some feet above sea level. That's the commonly accepted convention. We don't say above sea level all the time because everybody understands that's what we're using. Okay, so in this case, when I wrote this 14, if you go back and look at the video, I said 14 meters above the valley floor, meaning this is the valley floor. So we just arbitrarily defined both of these heights with respect to the valley floor, but the valley floor is totally irrelevant to this problem. What is relevant is the heights relative to one another. Okay, so in order to make this problem easier for myself, what I would do is come in here and say, well, I can make either of these 0, by the way. So like if I wanted to make the 14 0, I could do that and make this 5 become -9, but now I have an extra negative and that would just be silly. So we're not going to do that. What I would do is make the smaller one 0. So we've got this height becomes 0, and then just make sure you don't forget to make this become 9. And so then at that point, we're also able to eliminate height number 2 as well. And so then if we go ahead and pull everything down just to simplify it for ourselves, we've got GH1 is equal to 1/2 V2 squared, which is just so much easier to work with. And then we can simplify it further and go ahead and say that, all right, well, V2 is equal to radical 2GH1. And if we go ahead and plug that stuff into the equation, we've got radical 2 times 10 times h1 we said was now 9, right? So, well, 2 times 10 times 9, that's like, I don't know what that is. Was that 180? Radical 180. Right. And so now this brings up another point. I do recommend having some idea of some square roots for this test, or some perfect squares. Like, you don't have to know exactly what radical 180 is, but it is pretty helpful if you understand that the square root of, let's say the square root of, well, the square root of 13 is 100, or sorry, the square of 13 is 169. That's useful, because that's really close. Or you could say, well, we don't have another one that's like super close to that. I guess the next one would be 14. I don't remember what the square of 14 is, but what you could do is say, well, I know that this is between the 169, which is radical 13, and I know that it's also less than 200. So radical 200, you can make radical 200 become 2 times 100 in the root thing. And then what you end up with is 2 times radical, or sorry, 10 times radical 2, because you can pull that 100 out. And I definitely recommend knowing that radical 2 is 1.41 for this test. It's just useful to have that information, right? So then what you'd say is that would be 14. Obviously, that's not the thing that we're looking for here, but it'd be like 14.14 or something. Okay, so that again, I was just solving for radical 200. So our 180 is going to be somewhere between I don't know, 13 and 14, I would say. And the answer choices aren't going to be so close that you have to get closer than that. That would be silly. So anyway, that's how we go about solving that problem. So we'll say velocity v2 is like 13 and a half meters per second.
Do you mind if I say something?
Yeah, go for it.
So, can I draw on the screen a little bit?
Yeah, absolutely.
Okay, so when we're doing this, we have the potential energy is equal to this. So when you like do this step, like cross canceling things out, you would end up getting actually, height 1 minus height 2. And then of course the 2gh. So you can even think of that as 2g like delta h. But yeah, in general, this formula is super useful for a lot of questions that they expect you to answer using kinematics, but you can just use conservation of energy. So this would be just the velocity of something that is in free fall, or the velocity of something that goes from being completely 100% potential energy, because if the v1 is 0, that's a 0 kinetic energy. But if you have some potential energy and only potential energy, and then you convert that as something falls, this equation over here is super useful to use. I would say that even have that down in your memory.
Yeah, I totally agree with that. I thought I almost said it as I was going through, but I was also carrying a different concept, so I just let that one go. But yeah, you're spot on that. I totally agree. And keep in mind though, as long as your accelerating force is exclusively gravity, you can use that. So because the G, you have to account for something else. If gravitational forces or acceleration due to gravity is not your only source of acceleration, G can that factor would change some. But yeah, spot on. Thank you for that. So moving on to another example of conservation of energy. That's kind of like the consummate easy example, you could say. Because it's just ball rolls down a hill, ball is a discrete quantity, goes from no speed to some speed, or maybe some speed to no speed, or some combination of those things. This gets I find that people have a lot harder time with it though once they start having to consider it in the context of different systems. So we could think about like charges, or the one that I have on the top of my head right now is fluids. Let's see if I can recreate this problem, because I forgot, or my notes got deleted. I'm going to keep making that excuse, which is true. But okay, so our assignment here in this conservation problem is we've got a water tower that has a pipe coming off the bottom, and that pipe goes through the ground through a city and comes out the other end, and it shoots water out. Let's say that that's like a fire hydrant or something. Apologies for the super messy picture. So here we're going to say that this water tower in this case is, I don't know, go ahead and say it's like 12 meters tall above that little underground pipe part. And this thing over here is, we'll go ahead and call it 5 meters tall. We're also going to say that the radius of the water tower is 5 meters, and the radius of this pipe coming out of the ground is 0.05 centimeters. Oh no, that's really small. that's excessively small. Let's say 5 centimeters. All right. The question here is, how fast is the water going when it shoots out of this pipe? So basically, again, what is V2? Is our question in this situation. So very similar problem, but with a key distinction that is going to be really important. So does anybody have any thoughts on like how they would go about approaching this thing? Okay, so what you need to recognize here is that we no longer have a discrete mass that we're looking at. So this is, again, looking into fluid dynamics a little bit, which we've done some of already. But in this case, we need to come up with a conservation of energy equation that is useful for fluids. Some of you may already be aware that Bernoulli's law serves that purpose. However, I want to show you how you could, Bernoulli's law is like one of the longest equations, if not the longest equation you have to know for this test. And so it could be easy to forget. So I want to show you how to regenerate that and why Bernoulli's law makes sense, like the source of Bernoulli's law. So what we're going to look at here is that, well, if we rewrite the conservation of energy equation, so we've got mgh1 plus 1/2 mv1 squared is equal to mgh2 plus 1/2 mv2 squared. All right, so that's the conservation equation that we were looking at a little bit ago. And you would find that the mass, you could cancel the mass out of all of it, but you'll find that, you know, you don't have a discrete quantity of fluid here. And so this could be an issue if you needed to use it to solve an equation. There's also this third factor that you can put into the conservation equation, which has to do with ambient heat or ambient temperature, ambient pressure in the atmosphere surrounding you. So we can go ahead and just say that those are like, I don't know, we'd say ambient heat. I'm just going to put heat 2 and heat 1 in this case. And this is the more general version of the equation that accounts for non-conservative forces as well. And so then what I recommend doing for a fluids problem is thinking, well, the biggest difference between these two problems is that we had a quantized ball that rolls down this hill versus here we just have like a fluid moving and there is no necessary beginning or end to this fluid. So what I would recommend is making this specific for fluids. And the way that you do that in this case is by dividing the entire equation by volume, right? Because that is the major difference, is we didn't understand where our ball in this second example begins versus ends. So we're going to, by dividing the entire conservation equation by volume, what we're able to get is an equation that's actually useful for this fluid stuff. So here, I'm going to write it in like a different color so that it's obvious that you can all see it. So if we take heat and divide heat by volume, does anybody know what heat divided by volume is? Does anybody know what units of heat are? All right, units of heat are joules. Okay, so you know, heat, work, energy, all of that stuff is in units of joules. So if we take joules and divide it by volume, you might remember a little bit ago that I said that work equals pressure times volume, right? Or joules equals newtons per meter squared times meters cubed. Okay, so by dividing heat by volume, what we get here is like our ambient pressure. So we're just going to call this P1, ambient pressure, because we took newtons times meters and divided by meters cubed and got newtons per meter squared. All right, similarly, whenever we divide mgh1 by volume, well, mass divided by volume is density, right? So we can just take, instead of having mass now, we get our density, and we can go ahead and multiply it times g times h1. All right. The next expression that we get in here is 1/2 mv1 squared. And so if we divide that by volume, again, we put density into the equation. So we get 1/2 rho v1 squared. All right. So, and then we just do the same thing to the other side. Sorry, it takes a second to write this whole thing out. It's just annoying. Times 1/2 rho v2 squared. Okay. So this is Bernoulli's law. So the way that Bernoulli's law is derived is by dividing conservation of energy by volume. So now you can see that Bernoulli's law is just a special version of conservation of energy. You will be astonished at the percentage of equations that are relevant for the MCAT that you have to know that are just specific instances of conservation of energy just messed with a little bit. Like I already mentioned that the ideal gas law is that. It is just that. That's all it is. The equation for finding like height of fluid in a barometer is, again, just that. It's just all that is a simplified version of this one, actually, because in a barometer, you have no dynamic pressure. By dynamic pressure, what I mean is these two, the two that have velocity, these two are dynamic pressure. And so you drop that, right? And then you also drop, usually the barometer is vacuum sealed, so you also drop P2 out of it. And so you end up with literally, that's the barometer equation at that point. So understanding that is just huge on this test. Tons of other equations like that. And you can also start, when you get really good at this, making up your own equations for specific instances of problems. I never, ever, when I'm working through the MCAT, think, what equation do I have memorized that fits this situation? Instead, what I think is, what relationships do I know that I can make an equation from in order to most easily and efficiently solve this problem? That is so much faster and so much more reliable as well, because you're not putting all your chips on the notoriously faulty human memory. Instead, you're using your reasoning and critical thinking skills, which is what this test is out to reward anyway. So it's just playing the game that they're asking you to be good at. This next expression in here is just static pressure, just to go ahead and identify all of these, since these are super relevant. And then I always call this ambient pressure. I hear some people say that it's atmospheric pressure. Some people I've heard call it gauge pressure, which is not necessarily right, but there's it doesn't matter what you call it. Just understand that it's pressure due to the column of atmosphere above the thing. And so in this case, we're going to say that our tank is vented, meaning that the ambient pressure at the beginning and at the end of the pipe are the same. And so we can go ahead and get rid of both of those from this equation as we try to solve it. What other than variables can we get rid of in this? Anybody have any votes for variables to get rid of now that we've eliminated ambient pressure? So one of them that you can get rid of here, just like we did above, is density, because since we eliminated ambient pressure, all of the expressions left have density in them. So we can go ahead and cross that out across the board. We can also do the same thing with height that we did previously, right? So we can make this one become 0 meters. This one over here becomes 7 meters. If 12 minus 5 is still 7. I don't know if that's true. All right, what else? Is there anything else we can get rid of? We're trying to solve for V2, so can't knock that out. Another variable here then that is the least obvious one to get rid of, but is a super important intuition that once you start making these intuitions, that's kind of going to help you make the next leap on this test as you're getting better and better at this. The next variable is not actually 0, but we can approximate it to be 0 using that continuity equation that we talked about earlier. So notice here how the radius of the left side is enormous compared to the radius of the right side, right? So if we look at continuity equation, we'll call the left side A1 and V1 equals A2, V2. We're going to consider eliminating V1 in this situation, but I just want to show you why that works. So here we want to think about, all right, well, what is the ratio of, let's say, V2 to V1? Because we want to think, or we'll say, what is the ratio of V1 to V2, since that's the one we're wanting to assess that. So we'll say V1 divided by V2 is equal to A2 divided by A1, all right? Well, what are A1 and A2? Well, A1, or I guess we'll start with A2 since it's on top. A2 is pi times 25, right? Because it's pi r squared, so I already squared the 5. So pi times 25 is, oh, I'm sorry, that's the wrong one. That is A1. Pi times 25 is A1. And then A2 is, we said that the radius over here is 5 centimeters. So that's the same as saying 5 times 10 to the negative 2 meters. I would go ahead and I recommend just go ahead and putting it into meters. So then we've got over here, we have pi times, I said 5 times 10 to the negative 2, and we have to square that. So what we end up with here is still, we have both of those pi's, which we can just, completely cross out. And we end up with 25 times 10 to the negative 4 divided by 25. And so we find that the ratio V1 divided by V2 is 10 to the negative 4. And since all that's just being added to these other expressions, that is such a vanishingly small number that for the purposes of precision required on the MCAT, we can just throw it out. All right, so we can eliminate V1 for that reason, just because it's so small that to include it would just be a waste of our time entirely. So get rid of V1 that way. And so then what we're left with is, and remember Shane saying this was important, because what we're left with is G times H1 is equal to 1/2 times V2 squared, which, and this is why Shane was saying this is important, is because that all comes out to be V2 squared, or sorry, V2 is equal to radical 2 times G times H1. So it's like literally the same problem. That's why conservation of energy is helpful for solving problems that you don't know how to otherwise do. We can go ahead and throw the numbers in there to get something out of it. So 2 times 10 times 7, well, 7 times 2 is 14, times 10 is 140. So we've got radical 140. Well, 12 squared is 144. So we can say that this V2 is approximately 11.9 meters per second. Anyway, that's some info about that. Usually my impulse here is to go on to show you more fluid dynamic stuff, but that's not the point here. What we're trying to accomplish in this meeting is talking about tackling the chem phys section. So I would jump to the next, what I would recommend as the next sort of step in this hierarchy of things. So we went from units, conservation of energy. The next thing I think about is force equilibrium. So equilibrium is king on the chemistry component of this. I am thinking more about physics today, just because I think that that's where people have a hard time on chem phys specifically. Like if normally when I see somebody whose chem phys and biochem scores aren't the same and chem phys is lower, the issue has to do with physics typically more than it does chemistry. So that's why I'm kind of leaning that direction. But equilibrium is amazing for chemistry as well. It's also amazing for biology. To consider just the relationship between reaction quotient and equilibrium constant dictates so much of what you think about in biology. Like when I was in medical school, if I would forget to like learn mechanism of action for some drug, but I'm given a disease state and I understand the pathophysiology of that disease state, then all I have to do is, and I know that this drug treats this disease state, then all I have to do is think about, well, what would need to be done in order to mitigate the underlying pathophysiology of this disease, and then how would I shift that equilibrium, right? Because that's all we're doing. Most of pharmacology has to do with that. Most of medical intervention is just shifting equilibria in a direction that is going to be more compatible with, enhanced survival or quality of life, right? So like so much of this is just dictated by where we sit on the equilibrium, because we know that biological and physical systems tend toward equilibrium. Everything given time tends toward equilibrium, trends toward equilibrium. I guess those words both work there, but and so that's how it's relevant in the chemistry context. But in the physics context, it's going to be very explicitly tested for in your ability to assess both force acting and acceleration taking place, right? Because if you see a system where there are multiple forces acting on an object and your job is to predict direction that object's going to move or whether that object's going to speed up or slow down, then fundamentally what you need to be assessing is what the net force on that object is, both magnitude and direction, right? Because force is a vector quantity. So we have to think about both magnitude and direction. And so if you're able to assess or able to figure out that the net force on a given object is 0, then what you can know is that that object is not going to change its velocity. That is not the same as saying that that object is sitting still. Okay, this is very, very important. So velocity will be constant if force is 0. I did not say velocity will be 0 if force is 0, right? So velocity constant means force is 0. Force is 0 means velocity is constant. So if we already, I know I've said it 7 times, but if we already have a velocity and net force is 0, that velocity will just be sustained in perpetuity. And you could think, okay, well, what about like, if I shove my friend in their desk chair across the room, they're not just going to like run through the wall and continue on for eternity, right? Well, no, because there's friction, and friction is a force, right? And there's the wall. So that, like even if friction's not sufficient, the wall probably takes care of that situation. So I just recommend if units fail and if conservation of energy is not appropriate for the situation, assess equilibrium. Another insight to determining whether you go the conservation route or the equilibrium route is to look at the context of the question. If the question is asking you, if the question says we have this system in this situation, then we mess with it in this way, what's it like at the end? Then that is a conservation problem, because we have like situation 1 and situation 2. However, if the question is asking you, we have this system and these things are playing on it, what's gonna happen probably, or like what is the change resulting from this from this composite of forces, then that is more likely to be an equilibrium question. This is something that the reason we have you do like 5,000 practice questions leading up to your test, with the AMC plus our stuff plus UWorld, is so that you can get a good sense of how to use these things. I'm just giving you the tools right now, but you can be armed with like the best tools in the world, but if you don't know how to use them, they're not going to be helpful at all. So definitely do some practice problems from this stuff. So I've got some for the equilibrium thing. I probably have too many here, frankly. I pulled in a lot. But let's just look at a few of these. So, and this is what all my conservation stuff looked like too, by the way, before it all got deleted when my computer crashed 20 minutes before this meeting. Okay, so here we have a 5 kilogram mass that's hung from the right end of a massless meter stick, and that's attached to the ceiling 20 meters from its left. And I went ahead and just drew the picture out because I know that wording is kind of confusing. So first question here is, what mass would need to be attached to the left end to level the meter stick? So think about how you would go about doing that and try to vote. Yeah, vote on this one because, I gave you A, B, C, D. I'm going to give you all like 1 minute to work on this and to vote. Oh, okay. I just realized that you all, or half of you have voted. Yeah, you're all crushing it too, by the way. Everybody got it right. Can you all see the poll right now, like as the results tabulate? Or am I the only one that can see that?
I think you're the only one that can see that.
Really? Okay, that sucks. Okay, so we have 6 people have voted, and all 6 of you picked D to this point. 7, and 7 have picked D. So yeah, nice work. Does anybody want to say how they solved this? One of you who picked D on this. No pressure.
Joe, can you check your chat between you and me?
Oh yeah, for sure. Give me 1 second. Oh, weird. Some of you can't see the poll. Let me see. So I'm wondering. Yeah, I don't know why that's happening. I just closed it out. I'm gonna try to make a new one and see if that works. Because it may have been the case that some of you joined like after the poll was initially created. I do not know now though where the poll option even is. Oh, there we go. Okay, I found it. I mean, I can share the results like that. I just found that, so sorry about that for not knowing that ahead of time. Part of the reason we're doing this webinar is that we're going to be offering a course that is, I think we're going to do it over winter break, that is a crash course through all of this stuff. And so a lot of the reason that I'm doing this just for free for everybody is, one, to add value, because I'm trying to make this the best MCAT program that I possibly can, and I think this adds value, that you don't have to like pay for extra tutoring hours or anything, but also is to test a lot of this functionality. So anyway, I don't know if there are some of you, are there some of you who still cannot see the poll? Yeah, I just relaunched it. Let's see if that fixed it for those of you who couldn't see it before. Okay, well, anyway. Okay, so, and Emma said in the chat, okay, nice, awesome. Thank you, Shiva. Emma said in the chat that force times length equals on both sides of the pivot 20x equals 80 times 5. Yeah, perfect. Nice. Awesome. That's exactly how I'd recommend going about this. So yeah, I would say the equation you're looking for is the torque equation, which is force times the radius times sine of the angle here. And the sine of the angle is just going to be 1 because the angle is 90 degrees for each of these. And then we just look at force times length. And the thing that I would pay attention to on this, I would have never written anything out for this if I were solving this on the MCAT, because I would see that like, okay, well, we got 80 and 20. That's a difference of, 400% of the 20, right? So I know that my mass just has to be able to account for that. And so mass is 4 times the 5 kilograms. So yeah, absolutely right. You're all did an awesome job on that. I'm going to go and see if I can reset this for the next question on here. So next question on here is how does the situation change if we attach the mass 10 centimeters to the left of the string? So what I mean by that, in case it's not clear, is that we hang it, in this case, we hang it from here this time. So that's 10 centimeters there instead of 20. Yeah, nice. Okay. But yeah, I'll give you guys a couple more seconds to vote. Okay, so I've got some votes here for A and some for C right now. Give 10 more seconds to cast your final votes. There's a lot of movement on this right now. I wish you all could see it in real time like I can. That's weird that you can't. Okay. So, all right. So I just shared the results of this one. So we've got most people are saying A, but there's 33% of you saying C. The difference is here, both are saying that the mass needed increases, which are absolutely right, because the lever arm got shorter, so the mass needed would absolutely increase. But if you're using the same equation that you use, and you can use the same sort of setup or equation that you used previously, previously we had said 20 times x equals 80 times 5, right? Now all we have to do to change this up is say now 10 times x equals 80 times 5. And so then what you would find in this case is that x has to equal, not that, is that x has to equal, in this case, 40. Right? So here we would need a 100% increase in the mass of the mass of the thing hanging from the string, right? The reason that I wrote that is 2 of them as 100% and the others as factors of 4 is I just want to, this is a really low yield point, but I recommend being comfortable with interchanging between those two. So to say a 100% increase means that we doubled it. To say a 50% decrease means that we cut it in half. And so some people are just really uncomfortable with those. So, just so I guess. So yeah, A ended up being correct here in this scenario. I'm trying to think of what would have led people to say C. Does anybody who picked C want to speak up and like ask about why maybe you picked C? Just because I'd love to, to elaborate on why it's not C, why it's A, unless it all makes sense. Okay, nobody's saying anything. All right, so feel free to. Oh yeah, go ahead.
So I solved the first and second problem through the intuition thing that you did. So like 80 is 4 times 20. So just like by intuition, I was gonna pick 20. But someone in the chat said force times length. I'm confused in how length gets. Oh, is the length the radius? Okay. I had it like
Sorry, yeah.
Okay.
Yeah, R is, you'll find in the MCAT equations, R is used to denote a length a lot of the time. And the reason it is here in this torque equation is because frequently with torque, you're thinking about something being like, lack of a better word, torqued around a pivot point. And so the radius there is just the distance between like the pivot point and the outside of the arc, or where the force is acting.
Got it. Thank you.
Yeah, no problem. Okay, so next one here says, how does the situation change if we say the meter stick has mass, right? So notice here in this question it said massless meter stick, right? So there's specifically noted that the meter had no mass to it at all. How does that change? Or does it? Does it matter? Hint, if they tell you, it probably matters. If they go out of their way to print that. Oh, I guess I need to give you a new poll. My bad. Okay, relaunch poll. All right, go ahead and vote on that one. I'll give you like 10 seconds on this one. Only 2 of you have voted. 3. I'm going until we have 8 people have voted. 2 more, 1 more. All right, cool. So our results are here. One of you said it doesn't change. And then the rest of you said the mass needed increases. Yeah. Okay. So yeah, the 7 of you who said the mass needed increases are correct in this. The reason for that is because if the meter stick now has mass, you can assume, unless told otherwise, that the masses or the density of the meter stick is uniform throughout. That would be insane if they said that it wasn't. But and so in this case, the fact that we have more of the meter stick to the right of the string than to the left means that the now adding mass to the meter stick is going to have a disproportionate effect on the force pulling down on the right side. And therefore, you would need a greater mass added to the left side to offset the additional right side force from the meter stick in this case. So that's how that matters. I would predict that they would probably make the meter stick have a mass if they were to give you this on the MCAT. So in order to further assess that, you would just think about the center of gravity for each side of the meter stick. So I'll put this maybe like in this green highlighter here. So center of gravity is right here at 10 for this side, and it would be like here in the middle for this side. And so since the side on the right is 80 centimeters, we would find the center of mass to be at the halfway point there. And then we have to assume that the mass of the meter stick is like another weight that is hanging from that center of mass point. Right. So if we were to say that the meter stick had a mass of, I don't know, like 10 kilograms or something, then we would assume that we are assigning the mass of each of those to hang from there. So we'd say, well, we've got 80% of the meter stick over on this side. So we'd say you've got an 8 kilogram mass hanging here. And I'm just drawing it long because the 2 was in the way, and a 2 kilogram mass hanging here. And so that's how you would elaborate on this problem for the scenario in which the meter stick did have mass. And I just anticipate that being the way that the MCAT asks these problems, because the test has gotten harder year over year. And so, they're more likely to test things that way, I would think. All right, next one here. This goes back to what we were talking about with like area under a curve versus slope and all of that earlier. So the question is, I'm trying to get it all on the screen. That's super annoying. So the question here is, which of the following, meaning these following graphs down here, is an accurate representation of an object subject to the forces described by the graph above? So the poll's open if you want to vote at all. They love this kind of stuff, by the way. Also, you can vote for multiple on this one. I don't know if the poll is going to let you vote for multiple. I would like for you to vote for multiple. If you pick one of the 2 that are right, then you get credit, I guess, in the arbitrary credit that we're assigning. There are 2 that are correct. Okay, so when thinking this through, we see that the graph above, the one that we're referring to, has force on the y-axis and time on the x-axis, whereas all the answer choice graphs have velocity. And so we need to think about how force and velocity are related to one another, right? So force isn't directly related to velocity, I would say, but there is this equation that is force equals mass times acceleration, right? You could also think, well, I know that force is in units of newtons, and velocity is in units of meters per second, right? And acceleration is in units of meters per second squared. And so I know if I divide my newtons by kilograms, then I can end up with units of acceleration as well. So they're directly related. So whatever happens to acceleration also happens to force, and vice versa here. So you can just say where it says it's force, you can just say acceleration, right? And so then we can see that for the first half of this graph, force is constant. When force is constant, that means that acceleration is going to be constant. Acceleration is defined as the change in velocity per unit time. And so if force is constant, and if force is not 0, then that means that the velocity will not be constant. right? Because constant application of force means constant change in velocity. Okay, so anything that shows a constant velocity, which I think is just A, has to be thrown out right off the bat for that specific reason. Right, so here A shows, constant velocity both at the beginning and at the end, like pretty much the whole time. And somehow we just like randomly change directions. That would require like a huge spike in force right in the very, very center of this graph. And whatever we had would probably be broken. So anyway, that's how I would think about answer choice A. If again, we consider acceleration is constant and it's positive at the beginning of this, and then it becomes constant and negative at the end, then what you can say about velocity is that velocity has to be constantly increasing and then has to turn around and constantly decrease for the rest of the process. And so that matches graph B here. It also matches graph C. The reason that I made two that are the right answer here, well, one, I couldn't think of another wrong answer that was tempting, but the other reason, the main reason, is just to emphasize that we can have a change in direction of this object and it not necessarily violate the graph that we have above. So answer choice B in this case, and both, by the way, both B and C are correct. Answer choice B in this case shows that the object changes direction, right? If you look at it, it has a negative velocity, meaning you could think about it as like moving backwards at the beginning, all the way up until the like half a second mark. And then that velocity becomes positive, but force doesn't change because let's say we're going one direction, and at the beginning, all the way up into this like 1/2 point, up until that little green line I just drew, we're going in one direction, but we're slowing down. And then once we reach 0, we accelerate in the opposite direction we were going to begin with. C is also right. It's just less interesting because it doesn't show a change of direction until we get, well, it doesn't show a change of direction at all, actually, right? Whereas in B, we're changing directions at both of these green points, right? Where velocity goes from negative to positive, then positive to negative. Those are both changes in direction. Whereas in C, we're going the same direction the entire time. Both of them can correspond to that force graph. And then answer choice D here shows a constant velocity at the beginning, which is why we can throw it out right off the bat, because force is non-zero. And so if the force is non-zero, velocity just cannot be constant. And so that's how we can throw out answer choice D in this case. Okay, here's a barometer problem. So this is, again, just another equilibrium problem. You're using, in this case, Bernoulli's law, but you can just turn it into an equilibrium situation as well. I actually have, because I know that we're like at the 2-hour mark here, I have a video explaining this in your whiteboard videos folders. So just go there and look up the barometer problem in your whiteboard videos. It's just going to be a lot faster for you. I have, the explanation's pretty good. So I recommend just going ahead and doing that. This is the work. This is what it looks like at the end of the video. I just screenshotted it from the video. So just so you know, that's there. And then I have a few other, man, I really had a lot of problems in here, didn't I? I think that we might save these buoyant force problems for a different day as well, because I know that we're going to do a webinar on fluid dynamics. That's just a really difficult thing for people most of the time. And I don't want to make you all feel like you have to stick around in here for 3 hours today. And I also don't want to stay for 3 hours. I doubt Shane does either. So we'll come back and do more of that whenever we get into the fluid stuff. The buoyant force problems, the reason I had so many of those done there is that buoyant force tends to be the most challenging sort of equilibrium problem for people on this test. And so I think it does make a lot of sense to come back to that whenever we have more time on a different day. So I do have all of these prepared. I'll probably just punt them down the road to talk about it during the fluids webinar. I did want to do a biochem one next time because I've been very chem-phys heavy on the webinars. So we'll probably do next time, like, I don't really know yet. We'll do something in biochem. You can all vote. I also have this chem-phys passage to go through. I think what I might do on this, actually here, let's open the poll. All right, so vote in the poll. If you want to do the chem-phys passage now, vote A. If you want to do the chem-phys passage next time, vote B. Just because I don't want to make everybody stick around forever. Okay. 4, 5 of you have voted for A. I think A was now, right? 1 of you voted for B. And also, if you don't want to do it right now, you're welcome to leave. And we can not, and don't mean to be mean. I'm saying if you don't want to do it right now, if you have somewhere to go, this is all recorded, so we can just send you the video later. But yeah, it looks like 7 of you voted to do it now. 2 of you abstained, and 1 of you voted to do it later. So I guess we'll go ahead and do it now. I was going to use, I had a Kempf's passage plan to use for this that I realized last minute was from the AAMC exam. And I do not want to blow up one of the AAMC exams for any of you who haven't taken those yet. So we're not going to do that. Instead, we're going to use one from our practice test that we're working on. This passage is a work in progress right now. I only have 2 questions on it at the moment because I'm writing it and writing the questions out. But I think these 2 questions are both pretty indicative of the kind of stuff you're going to see on the MCAT, and specifically the second one is challenging. So I think this is going to give us some good insight into just like how to move through these things. So what I'm going to do here is show you how I would go through this passage, show you the things I might highlight, the notes that I would take as I move through it, and then ask for any questions on that. And then we can go through the individual questions that are here and talk about, the reasoning behind each of those. Please feel free to interrupt me if any of you have any questions at all throughout this. There's not very many of us in here right now, so it's totally fine if you want to interrupt me and say like, why did you do this way? Or why didn't you do this? That's the kind of stuff that we're here for. Chances are if you were wondering it, then somebody else is as well. So anyway. All right, so going through this passage to start out, first thing that I do every single time I get to any passage, ChemPhys, biochem, doesn't matter, psych-soc, is I look at the pictures. The pictures tell you so much stuff. This picture is kind of rough here because this is just like my placeholder picture, but this is supposed to say 1 over reaction velocity. And this graph down here is supposed to say 1 over substrate concentration. All right, so some of you may have seen the graphs like that in the past. And these are supposed to, the goal is to zoom in on this a lot more. You can see my axes are like way too big on this. But all said, it still should be, you still should be able to like get the info you need to from this. So first thing I see as I start to scroll through this is we've got compound Z. Okay, so I know already that I want to pay attention to what compound Z is. Okay, so sometimes I'll even like on my scratch paper, I'll write down like compound Z equal sign, meaning like a definition for compound Z for myself. Don't always come back to that, but it's something to be aware of. I also see Km and Vmax. And as if the Lineweaver-Burke plot below weren't enough to tell me that this is going to have something to do with kinetics, then Km and Vmax showing up there definitely would. And then I also see Ki. Ki is another constant. You're going to see a lot of like capital K subscript that you haven't seen before on this test. Ki really just refers to how much or how tightly the inhibitor binds to the enzyme that you're talking about. And so one thing that you can infer already without having read anything in this passage at all is that compound Z is an inhibitor of some enzyme, right? Because we were given a Ki, and when compound Z is 0, our Ki is not there. Ki is not relevant, right? Because there is no Ki if you have no inhibitor, right? It could be inhibitor, that we could have had the Ki for compound Y or whatever, and it's irrelevant because nothing's present. And then you can see that as we add more inhibitor, the Ki doesn't change. That is just an insight to the fact that Ki is an equilibrium constant. It's saying like this is the concentration we need of the inhibitor to reach 1/2 of our inhibition effect, let's say. And so Ki is not going to change relative to how much inhibitor you have present. And you can see that Km and Vmax both do change here. So another thing that I might note is that because Vmax is changing right off the bat, I know that compound Z does not bind to the active site. So I already know that compound Z is not a competitive inhibitor. It's not going to have any action at the active site, probably. So those are intuitions that I can get from looking at that table. And I promise it wouldn't take me 5 minutes to do that on a real passage as I'm going through. Oh, Shane, okay, yeah, you're welcome to head out. Sorry that this is lasting 2 hours. By the way.
It's been fun. Grateful to be here, and I'll see you guys next time. Okay.
All right, awesome. Thank you so much.
Yeah.
All right, see ya. Okay, so that's all of that stuff that I just said is having only looked at the table, and the tables are typically less useful even than the graphs. Like the graphs are a lot of times people freak out whenever they see a ton of graphs on one MCAT passage. The more graphs, the better, because picture's worth 1,000 words, and this thing's only supposed to have like 300 words in a passage on ChemPhys or biochem. So looking at the graphs is huge. Here on this graph, we can see that we have one dependent variable, right? That's 1 over reaction velocity. And so that should key you in to think about Lineweaver-Burke plot already, which is just like the double reciprocal version of the Michaelis-Menten plot. And then we can also see that we have substrate constant, 1 over substrate concentration is another dependent variable. So we can see that reaction velocity is going to change relative to substrate concentration. That's primary thing to be concerned about. And then we can also see that we have various different concentrations of compound Z. And another thing that I would notice is that those correspond to this table. So this is the same information, more or less. It's just presented in a very different way. This happens all the time and people don't pick up on it. So it's just like, if you understand the table really well, then you don't need to waste a ton of time on the graph. Similarly, if you understand the graph really well, then that can give you additional insights into the table. So I want to know like how inhibition of this enzyme varies with concentration of compound Z. I also want to know like what's going on with compound Z. I just want more information about that. I also know that this is not a competitive inhibitor, right? So what that tells me is that even though my graph is screwed up and we can't see the y-intercept, it tells me that the y-intercept is going to be different for each of these, right? Because if it was a competitive inhibitor, then they would all have the same y-intercept. And so that's just like another way that I can determine that this is not a competitive inhibitor, meaning that it's probably acting on some allosteric site. Okay, so, just more information that I can make myself aware of before I even begin reading. So now just notice how much I know about this. Granted, I wrote it, but I'm trying not to cheat in that way. Notice how much we know about this passage, having read nothing to this point. The temptation for a lot of people is to then go answer the questions and then just go cherry pick through the passage. That's going to work if you want to get like a few points and not touch your potential on the MCAT. I strongly don't recommend doing that. You can do well with it, and you've probably heard some people post on websites that they got 529 with never reading any passages and all of that. It's not real. Okay, just read the passage. The ChemPhys and BioChem passages are so short that it's not going to hurt you to read it. Just give it due diligence, read the passage, and then I promise you'll be better positioned to answer the questions once you do that. So we know everything about this passage now, or not everything. We know a lot about this passage, and so we can now read pretty fast as we go through it. So I'm just going to go through and show you exactly how I would read this, the things that I would pause on, the things that I would skip over, just to give you a sense of this. And again, please feel free to interrupt me throughout. All right, so this passage starting out says, recent developments in the field of enzyme kinetics have unveiled an intriguing enzyme named zeta lyse, isolated from marine microorganisms, blah, blah, blah. Okay, I don't care about the Pacific Ocean or anything for this. This is the ChemPhys section of the MCAT. All right, so not important. Then it goes on to say studies have found. Okay, when it says studies, I'm going to pay attention because the MCAT loves experimental design. So it starts telling me about a study or experiment that was done. I'm going to slow down a bit, but I would blow right over that first sentence. So it goes on to say studies have found that zeta lyse acts on the substrate zeta sub. All right, so we have our substrate and we have our enzyme. I might just go ahead and highlight those really quickly just to know where they are, which is a large aromatic compound. Okay, so that there's a really good chance that's going to be important. Large aromatic compound. I'm already thinking about like UV vis spectroscopy. I'm already thinking about like electrophilic aromatic substitution reactions it could ask me about if it wanted to go the OChem direction. Thinking that the molecule is planar because it's aromatic, right? So all of these things are already popping into my head as I'm going through this. Also thinking about hydrophobic interactions, right? Because it's saying zeta sub is a large aromatic compound. So that tells me that we probably have a high proportion of hydrophobic amino acids in the enzyme active sites. That's another thing we can think about. All right, I'm 2 sentences in and already predicting questions. So you want to get to a place where you can predict all of the questions when you read through the passage. Now I'm going to predict like 25 questions, and they're only going to be, well, in our case here 2, because I haven't written more yet. But just constantly be quizzing yourself on what they could ask and why they're telling you the stuff they're telling you. Because if you do that and get good at that, that's going to help you so much if you can just predict the questions that come up as you're going through. All right, so moving on. This says, however, this enzyme displays atypical behavior under various conditions, showing a potential allosteric site. We already know that this is an allosteric inhibitor, so that makes sense. Potential allosteric site, I've never heard of that before, frankly. But what I'm telling myself is that might not matter because a lot of this is supposed to be above your head. So potential allosteric site, maybe sometimes that allosteric site is blocked in certain conditions. And so I would already be looking for like what those conditions are as I read through. All right, so it goes on to say zeta lyse was initially studied in pure water, and its reaction with zeta sub was found to be slower compared to when it's present in a saline solution, indicating a potential influence of ions on the enzyme's activity. Okay, so what that tells you is that the enzyme is more stable in saline than it is in pure water, which makes perfect sense. Like most biological enzymes are that way. So, I really not care too much about that paragraph. That's just like true of enzymes. They're more stable in saline. That's why the solvent for life is not just deionized water. Don't drink deionized water. It's not good for you. It's just not what you're made of. And so like changing the salinity of a solvent is going to change the solubility of things in it. And it's also going to alter the strength of the intermolecular forces that determine the tertiary structure of zeta lyse, right? So if we change the salt content, we might get a totally different tertiary structure, which would make sense that the enzyme activity would decrease once we get into pure water. Okay, so that's just something else to be thinking about here. Further studies introduce compound Z, a molecule that shares structural similarities with zeta sub, but with a sulfate group. Okay, so what that tells me is that it's more soluble, right? Like compound Z has to be more soluble than zeta sub because it has a sulfate group where zeta sub does not. Sulfate is highly charged. Okay, so it's, yeah, just another thing to be aware of. Compound Z having a molecular mass of this, probably going to be important, but I'm not going to highlight it because like my eyes can very quickly find numbers whenever I jump back into the passage. So if I need to come back and look at that, then I can. Was observed to potentially bind to the enzyme's allosteric site, affecting its kinetics. Okay, so they just told us that it's not a competitive inhibitor, so it's binding to the allosteric site. We see our table that we already looked at, and just confirm what we just learned. We can also see that Km, as concentration of zeta sub increases, Km decreases. What does that tell us? So what does Km stand for? Does anybody just, you're welcome to say it, or I can tell you also. So Km is the concentration of substrate necessary to reach 1/2 of Vmax. That is its formal definition. Another way to think about it is inverse of affinity. So if the enzyme's affinity for the substrate is very high, then the Km is going to be really low. If the enzyme's affinity for the substrate is very low, then the Km is going to be very high, right? So in this case, we see that Km decreases as we add more inhibitor. What that tells us is that the inhibitor leads to an increase in the enzyme's affinity for the substrate. That is counterintuitive. However, if you understand that compound Z here is a allosteric inhibitor, then what you might note is that means it can bind to the empty enzyme, but it can also bind to the enzyme substrate complex. In either case, whether it's binding empty enzyme or enzyme substrate complex, the binding is going to lead to a conformational shift in that enzyme that is going to affect the enzyme's ability to bind to and let go of the substrate, right? So in this case, we see that the enzyme has greater affinity for the substrate when we have the inhibitor present. So that should tell us that the inhibitor is binding to the enzyme substrate complex, which makes it incapable of releasing the substrate or releasing the product. And so it slows down the reaction by making the enzyme grab onto the substrate harder, so it's no longer able to release it anymore. Okay, so that's how this inhibitor is working. Okay, so moving on from that. So it goes on to say, replacing the pyrrole and compound Z with a furan ring. All right, so pyrrole, furan ring, those are probably important because those are functional groups you're responsible for knowing on this test. A pyrrole is a 5-member nitrogen ring. So it's a heterocyclic 5-member nitrogen. It's aromatic. So that's what to know about that. A furan ring is the same thing exactly, but just with an oxygen. So I'd be quizzing myself on that already. These are things that you just have to have memorized. This is kind of goes into that category of just like really annoying things that you need to know and then forget right after this test. I strongly recommend doing both, learning them and forgetting them as soon as the test is over, because you'll like never use this again. So pyrrole ring, compound Z, furan ring is compound Z1. All right, so now we have Z, which is pyrrole, Z1, which is furan. I would have in my notes, I'd go ahead and say Z equals pyrrole, or you could even say like Z equals nitrogen and Z1 equals oxygen, right? Because that's the only difference. They're both 5-member rings. So just making note of that. Then the passage goes on to say, upon further investigation, introduction of compound Z at concentrations of 50 and 100 micromolar. Oh, sorry, compound Z1. Whoa. That's annoying. Give me 1 second. I don't know why that happened. Okay. Introduction of compound Z1. I would highlight that here just to make sure that I'm aware that it's talking about Z1 instead of Z up there. At 50 and 100 micromolar, resulted in kinetic data which proved statistically indistinguishable from those seen with 0 micromolar of compound Z in graph 1. All right, that's a lot of words, but fundamentally all it's saying is that compound Z1 doesn't do anything. that's like, just reword it, and it's like compound Z is not an inhibitor. So let's say not inhibitor. So what that tells us, if we change the nitrogen out for an oxygen and that makes it lose its ability to inhibit the enzyme, what that tells us is this nitrogen here is important, right? So like think about ways that that nitrogen could interact with, in this case, the allosteric site, right? Not the active site, because we've established it's not a competitive inhibitor. That is important for this passage. All right. So then it goes on to show us this graph, and it said that compound Z1 is indistinguishable from this blue line right here, which was just or 0 micromolar compound Z. So basically 0 micromolar compound Z is another way of saying that the native enzyme without the inhibitor present. All right, so now we know all of this stuff. We took a few notes. We highlighted like 3 things. Notice I highlight like very, very little as I'm moving through this. I think that highlighting half of the passage is a huge waste of your time. I'd rather you just not use the highlighter if you're going to do that. That's a hot take, but I promise that it feels a lot better whenever you can trust that the things that you highlight actually matter whenever you're going back, rather than just like highlighting to make yourself feel busy as you're reading. Rather than highlighting to feel busy, just like pause and think to feel busy. I promise it'll be a lot better for you. Anyway, so moving on to these questions. This first one here. So we went through all this like enzyme kinetic stuff. Frankly, feels like it should belong in biochem, but those 2 sections bleed together so much. Part of why I did this. And then they can ask you all sorts of questions from like strictly chem phys, even though the passage feels like it should be from biochem. So here, this question says, using the data in table 1, what is the mass of compound Z required to prepare 250 milliliter solution with a concentration equal to Ki? All right, so how to approach that? Well, in cars, I always recommend, on the cars section, I always recommend reading the question, pausing and asking yourself what that question is actually asking, redefining the question for yourself, simplifying it, putting it in your own words so that you know what your assignment is. And then making a solid prediction. Then and only then making a solid prediction. And only once you've established a solid prediction, and I mean a solid one, not just like, I don't know, I'm looking for a number, right? Like an actual solid prediction. Then you go look at the answer choices. That's for cars. For chem phys, biochem, psych soc, the method is very much the same, except I do recommend taking a look at the answer choices, not like specifically analyzing each one, but just seeing like, what is the format of my answer choices? Here, for instance, we can see that all of our answer choices are numbers, so we know we're doing a calculation for sure. However, we can also see that 2 of them are kilograms and 2 of them are milligrams, and the numbers aren't the same across those. So there's probably going to be 2 of these that are really easy to throw out as we go through. So that's just another, added context for this. I would track my units as I do this calculation for sure, just always to check work, but also just to make sure that the number I end up with, I'm confident that it's kilograms over milligrams or vice versa. Okay, so just a few tips going into this one. The question is relatively straightforward here, so there's not that much extra interpreting we need to do, but we do know that we need to be finding how much compound Z we need. So we're looking for a mass of compound Z, which is why we have kilograms and milligrams, that is necessary to prepare 250 milliliters of solution with a concentration equal to Ki. All right, so then what is Ki? Well, you have a table that shows you what Ki is. Even if you don't know what Ki is, though, you can still calculate that. This still works perfectly because of the units thing that we talked about earlier. So we know we need to go to kilograms. We know we're starting in concentration units, which are micromolar here, right? So we've got Ki is 52.5 micromolar. Okay. So I know I need to get into either kilograms or milligrams. I'm probably just going to head to grams and then see where I need to go from there, just to like not bias myself in one direction or the other. So we've got 52.5 micromolar. That's the same as saying 52.5 times 10 to the -6 moles per liter, right? I'm going to move this down because I know I can see that we're going to run out of room already. So 52.5 times 10 to the -6 moles per liter. All right, well, I want to get rid of those liters because I know that we don't have a volume in the answer. So I would go ahead and do that. And it tells me 250 milliliters of this thing. So I would think, all right, well, they gave me milliliters. I have liters that I want to get rid of. So I know that 250 milliliters is 0.25 liters. Okay, so I would just go ahead and put that in, 0.25 liters. And that's over nothing. It's just over 1, right? And so now my liters are gone. Now I'm in moles and I need to go to grams. and molar mass is the way to do that. Like, that's relatively straightforward. So I'd say my 456.7 grams per mole. And notice I wrote it this way. If I was in grams trying to get to moles, I would have flipped it, right? I would have put the grams on bottom and moles on top, because we need to have these things on opposite sides of the fraction bar. This is useful to review no matter how good you are at math. So anyway, so now what we've done is we've canceled out all the units, and we can see that we're in the right units moving forward. However, this calculation sucks. So I would recommend rounding some of this stuff. This is where the rounding thing that we talked about earlier comes in to play. I would probably, in this case, round both of those numbers, both the 52.5 and the 456.7. You can, if you want to be as accurate as possible, just round them in the same direction, or round them in opposite directions, but with similar like amounts. Or you can just round them in the same direction and know that you're definitely going to be either over or under whatever answer choice is relevant here. But you can also see that your answer choices are far enough apart that just like rounding a little bit isn't going to matter very much, because like even if we round down to 50 and up to like, or down to 50 and down to 450, we've definitely not doubled the value of any of these, right? And so since we haven't doubled their value, notice that the answer choices are all just doublings of one another, starting at D, going up through A. So we know that we can be relatively confident in what we end up with here. So I would say like, just make this 50 times, I would say 50 times 0.25, or I would even make it like 1/4. So like 50 times 1/4, which is what 0.25 is, times, I guess we'd say like 450. And so then what we end up with in this case, well, let's see, 50 times 450, that's just super fun to work with. I'd go ahead and make it, I'm going to go ahead and make it 400, just to like make life super easy. And I just want to also emphasize like that you do have the room to do this. So 50 times 1/4 times 400, well, 1/4 times 400 is going to be 100. So then we end up with 50 times 100. 10 to the 2. And then we also don't forget about that 10 to the -6 that we needed to bring down with us as well. So then what we end up with here is 50, and note that we're in grams here, 50 times 10 to the 4, or sorry, 10 to the -4 grams. And there's only one answer choice that works with that one, right? So just by the coefficient alone, we can look at C, and then I would just check that using the orders of magnitude, be like, okay, well, this is grams. So 50 times 10 to the -4 grams is the same as 50 times 10 to the -1 milligrams, and 50 times 10 to the -1 equals 5. So we ended up with 5 milligrams. And notice like it's not ambiguous at all. We rounded a ton on that. So don't be afraid to round stuff. I can't emphasize that enough. Right, so C ends up being correct there. Oh, thanks for voting, one person who voted. It's my bad for not telling everybody that we were voting. Okay, we'll vote on this next one. So this question is a lot harder. This is the type of question that most people really struggle with on this test, which is why I wrote this. All right, so this question says, based on the information and data presented in the passage, which of the following are plausible hypotheses for the differences in kinetic data observed in the presence of compound Z and compound Z1? And then it gives you all these Roman numerals. All right, so this is really challenging, because if you start assessing these answers or these Roman numerals, like each of these is kind of like its own question. And then you have to come up with the combination of those that is correct. Frequently, Roman numeral questions are easier depending on how they give you the Roman numerals. Like, for instance, if number 1 turns out to be wrong here, then whatever, just pick D and move on. You don't even have to look at 2 and 3. I probably still would check them, like just to be safe. But that is my general recommendation for the Roman numeral questions. In this case, though, it's really important that we identify what this question is actually asking us to do. So based on this question, if we go back and restate what the question is asking, it's saying, which of the following are plausible hypotheses for differences in kinetic data observed in the presence of Z and Z1? All right, so it's saying differences in kinetic data with Z versus Z1. Well, what we see in the kinetic data is that compound Z inhibits this enzyme. Compound Z1 does nothing to it, right? So we need to come up with an explanation for that. Like, why is it that Z is able to inhibit the enzyme and Z1 is not? whenever they're basically the same compound. All we've done is trade out a nitrogen for an oxygen in that chiral ring. Okay. So answer choice 1 here, or whatever, Roman numeral 1 here, says the sp2 nitrogen atom in the heterocyclic ring of compound Z forms a coordinate covalent bond with a known cofactor of zeta lyse. Right, zeta lyse being the enzyme. So what do you all think about that one? I wish we could have like an actual discussion on this, but sp2 nitrogen, what's that mean? Well, it means a nitrogen that has fundamentally like 3 things on it, right? So those could be 3 carbons, they could be 3 hydrogens, they could be, well, probably not 3 hydrogens, they could be 3 carbons, they could be like a double bond to a carbon, a single bond to another carbon, and a lone pair. You know, that would be sp2. So the chiral ring itself will frequently look like this, where it either has like lone pair here and bond like that and that, or it'll have a hydrogen attached to that, and the bonds will be like here instead. So that is the chiral ring. So we know that the nitrogen is sp2 hybridized in the chiral ring. So we can say that that part of the question, the answer is right. But does that actually answer the question? And so the question again is asking about differences in kinetic data between the inhibitor and the not inhibitor, right? So it says sp2 nitrogen, the heterocyclic ring of compound Z, forms a coordinate covalent bond. What's a coordinate covalent bond? A coordinate covalent bond is a covalent bond, meaning sharing of electrons between 2 atoms, in which both electrons come from a lone pair of the more electronegative atom. And so you typically see this in things like nitrogen or things like oxygen forming covalent bonds with transition metals. Heme in heme and hemoglobin is like one of the best examples. Cobalt does this a ton. And so we don't know what all is happening in this in zeta lyse. We don't know anything about cofactors of zeta lyse, but what we do know is cofactors are metals. And we also know that this nitrogen does have a lone pair, and it is sp2 hybridized. And it's also not present, and this is key, it's not present in Z1. And so we've stated things that we know to be true about this nitrogen, and we proposed a way in which those things that are true of that nitrogen would exert an effect on zeta lyse that is not possible given the oxygen and the furan ring. And so all those things considered, compound 1 or hypothesis 1 is solid. Like, we can't say whether it's true or whether data would support it or not. Like, we need to do the experiment, but this is an experimental design question, and I can't poke any holes at all in hypothesis 1 just from a logic perspective. And so that answer choices, or this is definitely right. So at this point, kind of sucks, we can't eliminate other ones, but we know D is wrong. And so now what we can see is that we need to assess 1 only, 1 and 2, or 1 and 3. And so if you move down and find that 2 is right, we don't even really need to look at 3 as long as we're confident 2 is right. Or we could start with 3, and it's slightly longer, but we can start with 3, and if we know it's right, then 2 is definitely wrong. But if 2 is wrong, then we don't know about 3, and so we still need to check it. So anyway, let's go ahead and look at both of these. 2 says the furan ring in compound Z1 renders it incapable of interacting with the active site of zeta lyse. All right, go ahead and vote for this. A says that this is good, meaning that you would pick B, I guess. But vote A if you think that this is a good hypothesis. Vote B if you think it's not a good hypothesis. Okay. So of you who voted, we had 6 people vote. 4 of you said B, it's not a good hypothesis. 2 of you said A, it is a good hypothesis. So we know that compound Z1 has a furan ring and compound Z has a chiral. And so far, this is good. Everything about this statement is good, except one issue. Remember, I've stated this multiple times here. Compound Z is not acting on the enzyme active site. Compound Z is an allosteric inhibitor, meaning that the chiral ring in it interacts with the enzyme's allosteric site, not the active site. And so we don't care whether the furan ring binds to the active site or not. In fact, even if let's say that this statement is true, let's say that the furan ring can interact with the active site, the kinetic data would still be different. If it can't interact with the active site, the kinetics data is still different because it's a furan ring, right? It's not the chiral that we're talking about. So whether the furan ring can or cannot interact with the active site is totally irrelevant and does not matter at all for determining whether this for determining what's going on. And so therefore, this is not a hypothesis that would win you any grants. So we can go ahead and rule out 2, and that allows us to cross out answer choice B here. So what about number 3? I'm relaunching the poll. Go ahead and vote A if you think number 3 is a good hypothesis, B if you think it's a bad hypothesis. Looks like you're pretty evenly split here. I'm giving you a second. I think there's 1 or 2 people left. All right. I'm going to close it in 5 seconds. 4, 3, 2, 1. Okay. So these are the votes we got. So 4 of the 6 of you who voted said that said that number 3 here is a good hypothesis, meaning that you would pick answer choice C and move on with life. The other 2 of you, 33% of you, said that it's not a good hypothesis, meaning you would pick A. Okay, so compound Z has a higher affinity for the enzyme substrate complex than for the empty enzyme alone. This is perfectly consistent. This statement is perfectly consistent with the data that we observe here in this table. Remember, I said that increasing concentration of compound Z leads to a decrease in Km. What that means is that compound Z is binding to an allosteric site on the enzyme substrate complex. So compound 3 is statement 3 here is a true statement. Compound Z has a higher affinity for the enzyme substrate complex than it does for the empty enzyme alone. Just because it's a true statement does not mean that it answers the question, though. So 3 is wrong in this case. It's a true statement that fails to answer the question, because this is a comment on a fundamental characteristic of compound Z with no reference whatsoever to compound Z1, right? This is the question. Go back to the question stem. When you're torn on these, or when you spend a long time on a question, always go back to the question stem to make sure that you still understand the assignment. The question's asking you for plausible hypotheses for explaining the differences in kinetic data from compound Z and compound Z1. Just stating a true fact about compound Z is not sufficient to explain why compound Z1 demonstrates different kinetics. Now, we can modify this statement to say compound Z has a higher affinity for the enzyme substrate complex than for the empty enzyme alone, and compound Z1 has no affinity for the allosteric site, or something like that. That works. That would be a plausible hypothesis. We could test that hypothesis, right? We could do some sort of like mass spec and see whether compound Z1 shows up in the allosteric site or whatever. There's lots of different ways of doing this. I'm not an experimentalist, definitely not a physical chemist by any stretch. I never even took a class on that. But so do you see what I'm saying here? This is the reason I wrote this question like this and wanted to present it today in this meeting is because this is the type of question that everybody gets destroyed on. Like, getting these questions right is the difference between doing exceptionally well on this test and just doing okay on the test. Like, you can still do decently well on the MCAT and miss a lot of these just because they are the hardest questions and most people are going to miss them. But you really have an opportunity to set yourself apart by getting good at these. And it all comes back to restating that question in your own words prior to making a prediction and prior to meandering through the answer choices. So again, just very important. This is a CARS skill, right? Like, this is straight out of CARS. Understanding the assignment before you make a prediction, before you pick an answer choice. So in this case, this is incorrect because even though it is a true statement, it does not actually address the question. I know I've said that 35 times, but just trying to reiterate it over and over again. Does anybody have any questions on that? Because I could see this like upsetting people on this one. So I'm happy to hash it out with you because I made this question, so it's all my fault. All right, cool. No questions. All right, so that is it for the stuff that I had to present today. I apologize for the conservation of energy problems vanishing and me having to make them up as I went, but I'm happy to answer any questions. I know this has also gone like quite a bit longer than we anticipated it going. I need to figure out a way to like get these under time. So I'm happy to answer questions right now. You're welcome to just speak up, unmute yourselves. I think that's a lot easier than typing it in the chat, although you're welcome to type in the chat too if you want. I'd also love to hear any feedback any of you have, like, even if you have no questions, like, this is too long, make it short next time, or we'd like to see a different way of approaching this. Thank you, Emma. I really appreciate it. Yeah, so the goal here is in ChemPhys, it's really important to do practice problems because you can sit and read about the theories and the equations and all of that a ton, but going through practice problems is where the rubber meets the road, and it's a test of whether you truly do understand the concepts. Yeah, I think I might. I think Ray, I think I will do biochem next week just because I've been very heavy for ChemPhys. I think I've done 5 of these now, right? I think this is the 5th one, and I think 4 of them have been on ChemPhys. So, yeah. All right.
Have you ever thought about using practice questions from previous AAMC material?
Oh, have I thought about it or
Yeah.
you
Yeah,
mean,
like I found you breaking down the question extremely helpful. And like if you uh the conceptual part was really amazing in the beginning. It really broke it down everything. But then being able to like apply it into the question was like it's like a whole different ball game in my opinion, sort of.
yeah, it's
So I'm going go
oh, go
ahead.
ahead. Sorry. I didn't mean to interrupt you. No, go ahead.
I was just gonna say, like you being able to apply that question and to apply that conceptual knowledge into like an MCAT style question, I think would be amazing, like how we did here, sort
Okay.
of.
Yeah. Yeah, absolutely. And goal is to make these as much like the MCAT as I can, but everything is going to fall a little short of the AAMC just because it gets to decide what gold standard is, so that's unfair. But yeah, I actually did have a AAMC passage that I was going to do today, and then I don't know why it took so long to dawn on me that I don't want to mess up the AAMC exams for people who haven't taken them yet and who are going to be using them to assess like where they are in the process and stuff. But yeah, I mean, I do that all the time. So I've done it for like most of the AMC passages, I would guess it's, some point in time. I've thought about one thing that we've thought about doing is going through and just making a set of videos to explain all of them at some point. The AMC is pretty opposed to people doing that if they are trying to monetize it in any way at all. And so for me right now, the only reason we haven't done this is just a time and money thing, frankly. We will do it at some point, but it's just right now we're focused pretty hard on writing our own questions just so we can get these practice tests out for people who are retakers and stuff prior to the January test dates. We will do it in the future. And if you want, I'm happy to go through some of that stuff. Yeah, I know Kaplan does. They what their argument is that they're not monetizing it because they argue that they provide it for free. We are just not in a position to go toe to toe in a legal battle with the AMC right now, and so that's why that's why we haven't gone about doing that yet. We will at some point. I also don't want to do it. I don't want to halfway do it, if that makes sense. Like if we're gonna do it, I want to do it all the way right. And from my perspective, it's likely to cost tens of thousands of dollars to get that done. And so I just want to make sure that we're, not going to bankrupt the company to do it. Yeah, Shane just recently joined us, but he's taught MCAT for quite some time. He's going to be in all of these probably moving forward. He's coming on full time with us. So he's going to be doing a lot of stuff pretty soon. Today's actually his first day. He just signed his contract today. So that's where we are with that. Any other questions or feedback? Rup, I really appreciate the feedback. Like seriously, any feedback I can get is super helpful for me on this.
I just had a question about the crash course you were mentioning earlier. Will we have access to that for like if we plan on testing in January or March, or do you know how you
Yeah, that's a fantastic question. We're trying to figure out exactly what that course is and is not going to include. The idea with that course is to provide a lower cost item for people who want to work with us, but can't afford one-on-one tutoring or and also for any of you who are interested in doing it. I think that we're going to have to charge some amount of money for that course. But my plan is I think I think like Kaplan's course is like $2,500 and Jack Weston's like 2,000 or something like that. My plan is to undercut this in a comical way. So I want to make it what I have in my mind right now is to make it about $1,000 and for people to get access to like all of our stuff and everything, and also to offer it for all of you who are already doing tutoring with us at like some really kind of silly discount. I'm like what I have, and don't hold me accountable for, I haven't run numbers on this yet. I'm still trying to conceptualize everything, but what I have in my mind is to offer the course for either $1,000 or $1,200. Those are kind of the two numbers I've been back and forth between, and to give all of you at least a 50% discount on it, just because you're already tutoring students with us. And this isn't going to affect the webinars. I'm still going to keep doing these webinars at the same rate, but this course is going to take me a ton of time. Very frankly, like I'm going to have to put in, it's probably going to take me 100 hours to get it up, but it'll also include like all of access to our practice exams and access to a portal where you can watch all the videos and all of that. Also, tell me if that seems unreasonable or if that seems hyper reasonable or anything in between, because talking to all of you is the best way for me to figure out if what I'm doing makes sense.
I mean, I feel like $1,000 for a crash course is a pretty good deal. And then if we're getting that discount.
Cool. Oh, is Jack Weston full course 1,500? I thought it was 2,000 some. I think they have a course that's 1,500. I could be wrong though. I don't look that much in it. We can ask Shane. That's that's where he came from. Oh, the asynchronous course. Yeah. So this is what I'm talking about is a synchronous, like live online course, like what we're doing now, but meeting like 2 or 3 days a week with a syllabus laid out and all of that stuff. And all the videos provided and all of that stuff. Yeah. So that's, yeah. Thanks, Alyssa. Yeah. That 2K one is the one that I'm talking about. Because this is what I'm thinking on this. What I have in mind is about also, yeah, give me feedback on this too. What I have in mind right now for this course is like 3 days a week for like 2 hours per meeting for all of winter break. And so come out to be probably like 30 to 40 hours, something like that. And as sort of like a really hard crash course leading up to the January test dates, but also that you could take, and prep for a March test date or April or May or whatever. And then we're going to run it multiple times after that, because once I've done it once, it'll be easy to do it moving forward. And I taught Kaplan's course for 4 years. Like I know how this stuff works and know how to make it good. It's just a matter of doing it.
That sounds like a good time point. 30 to 40 hours.
Awesome. Thanks. Yeah, I really appreciate that too. So do you think that like 3 meetings a week at 2 hours a meeting would be good, or is that too many? Or would you rather see like 2 meetings at 3 hours per meeting? Or I just like whatever works best for all of you is the way that I want to go, because like if I make the course stupid, then nobody wants to do it. So yeah.
I think people stop losing. I think like most people, at least myself, like their attention dwindles after 2 hours.
I totally. Yeah, that's why I was thinking 3 2-hour sessions instead of 2 3s. Like obviously 2 3s is easier from my end, just because I have to show up less times. But I think there's more value to be had in 3 shorter sessions.
Oh, you'll be teaching these?
I'm going to teach at least half of them. I'm probably not going to teach. I almost definitely won't teach Psych Soc. I have a couple people who are better than me at that, frankly, and I'm pretty rusty on all that content because people don't ask me about it that much, and I never even studied it for the MCAT. Like it wasn't on the MCAT when I took the MCAT. Like I did take the 500 the one that you all take now. I took it a year and a half ago, and I did get a 528 on it, but I also did a psych rotation in med school, and I took psych classes in med school, and I went to med school, so like I have all these unfair advantages, but it just makes me not the best person to teach psych. So I won't teach that. Probably going to ask Simona to teach that. I don't know if any of you know Simona, but probably will ask her to teach that. She also really wants to teach a couple of meetings on just test strategy. She's really, really good at that. And then I don't know who will teach cars yet. We're thinking about a couple different options for teaching the cars stuff. Might be Nilam, might be Alex might be some combination of those two. Just kind of depends on who has availability and who wants to do it also, because it is going to be a lot of work to just pre-plan the meetings and stuff.
Yeah.
But I'll teach at least half of it, I think. Yeah, absolutely, Alyssa. Alyssa asked if one of the webinars could be on test taking strategy. Oh, you mean like one of these webinars? Yeah, sure. I was trying to kind of build that in throughout today, but I can talk to Simona and get her to do it. It's just a matter of getting her to do it. I don't know if she's going to be available on weekends or whatever, but yeah, I think that that's a really good idea. And then Deepali said, are there any resources that would recommend other than AAMC and UWorld for practice questions? I think those are the best two to start out with. The Exam Crackers book, if you're looking for practice questions that don't have passages associated, that are just like practice questions, the Exam Crackers books have phenomenal practice questions in them, but they're just like standalone questions. So it's good to like test your understanding of things, but it's not like MCAT style stuff. I've had people take the Altius ChemPhys and biochem sections before, just as like alone, to not to get like a full length score, because they'll obviously be deflated, and those are really excessively difficult. Like I can't imagine the MCAT ever being quite that crazy, like detail oriented and difficult, but it is a good way to challenge yourself and just get some additional questions. But I lean heavily toward UWorld when you're not doing AAMC, just because while UWorld is not quite like the real MCAT, like they've not really tried to be like the real MCAT. I don't think you may notice that their questions are way too long. Like the question stems are way too long in UWorld compared to the real AAMC stuff. I know this because we did an assessment of every question the AAMC has released and got like a character count on all of them and found a standard deviation. This is something I've been doing to prep these practice exams, and UWorlds are like double long, but their explanations are just so good, and there aren't a ton of fantastic explanations elsewhere. So that'd kind of be my hierarchy of recommending, is like UWorld and AAMC are up here, and then you can start adding things on for various different reasons, but everything is going to fall a little short of the AAMC in various different ways. Can we have the test strategy course early on in the crash course? Yeah, for sure. Yeah, I think, Emma, that's a great question. Yeah, I don't see why not. I think it would make sense to put it early. I think probably what we would do is have multiple sessions of the strategy component. We'll have one early, probably like maybe like first or second meeting, probably first meeting going over cars. Second meeting could be like some strategy stuff. I need to build out the syllabus for this still. Because I want to give you the basic strategies up front so that you can start practicing them as early as possible. And then we'll come back with additional strategies later. This is how I tend to try to teach this stuff anyway. So yeah, it's a good idea. Let me know if
I have to go, Joe.
Oh yeah, no problem. Yeah,
I have to go, but I really wanted to quickly just go over this first Roman numeral in question 2. Why how did you validate the cofactor of zeta lyse? Like, can you explain that?
Yeah. So these are meant to just be hypotheses, meaning that like it's not necessarily true. It is an explanation that is consistent with what we're able to observe and what we know to be true. So whether zeta lyse actually has a cofactor or not, we can't really say. But the reason that I wrote cofactor there instead of just like with zeta lyse is to also test the coordinate covalent idea. So a cofactor cofactors are usually transition metals that go into the enzyme. And if it forms a coordinate covalent bond with the cofactor, then that's probably going to alter the oxidation number of that cofactor, which is going to alter the way that the cofactor interacts with the organic enzyme. And so it's going to change the conformation of the enzyme.
Okay.
Yeah. And so whether it binds to a cofactor or not, the first step in doing this experiment would probably be to determine whether it binds to something. And then if it does, then you can determine whether it binds to a cofactor or if it is doing something else. Maybe it's having like an acid-base reaction or something, something like that.
Okay.
Yeah. So just because it's a plausible hypothesis, the operative component there is plausible hypothesis, not which of the following is necessarily true.
Got it. Okay. Yeah. So thank you.
Yeah. Thanks for asking though.
No. Have a good day, Joe. Thank you.
I appreciate it. Thank you. You too. Let's see. Let me know if there are any questions that I didn't address as I was answering these. Yeah, thank you all. I really appreciate it. And I really appreciate the feedback too. This is super helpful for me.